So I will start the session with a project overview, very briefly, to the ones that do not know the project. It's BIOCON-CO2 is the aim or the goal of the project is to transforming raw CO2 waste from iron, steel, cement, and electric power into industries into value-added chemicals and plastics. It was a project funded in the program Horizon 2020. The title of the topic was Microbial Platforms for CO2 Reuse Processes in the Low Carbon Economy. The project starts in January 2018 and will finish this June after 54 months of hard work of all the ones that we are here. We are 88 partners in the consortium, located in 8 European countries, and the budget of the project was almost 7 million euros, and it was coordinated by LITAT. The focus of the project was to reduce the greenhouse gases emissions and avoid overexploitation of natural resources. We expect to impact converting CO2 from fossil fuel burning into valuable commodities and support EU as a global leader in CO2 reusing technologies. And our core activities is to develop and validate in an industrially relevant environment a flexible strategy to biologically transform CO2 into value-added chemicals and plastics. The objective of the project was to develop and validate a platform of flexible and versatile techniques capable of using biological processes to transform real CO2 from waste, CO2 waste from iron, steel, cement, and electric power industries, as I said, into added chemicals and plastics. Generate new knowledge that can help to develop commercially viable strategies for reducing Europe's dependence on fossil fuel resources, and also increase the sustainability of the chemical industry, providing support for European leadership in CO2 reusing technologies. The project was the structure of the project was this one. We have two work package one for the management, but the technical work packages were the structure of the project was this one. We started with this work package 2. With the objectives to analyze the gas composition of the different industries that I have mentioned, also determine the gas requirements of the different microbial cell factories, enzymes, and microorganisms that we are using in the project, try to match the needs of the microorganisms and enzymes with the composition of the gases, and gas mixtures are also proposed in order to make these links. And also, we have investigated in several CO2 solubilization strategies. Later on this afternoon, you will, in the science sessions, you will see some examples of the techniques and the strategies that we have developed for that. Then there are 3 work packages running in parallel, where we develop the microbial cell factories itself. One, the BP3 is based on Clostridia strains. It's an anaerobic microorganism for producing C3, C6 alcohols. In BP4, we are using an aerobic microorganism, Cupria vidus, in order to produce bioplastics. And in BP5, we have 2 different systems, enzymatic systems, biocatalytic systems, in order to produce formic acid and lactic acid. Again, in this work package 6, we investigate in different strategies for downstream purification and validation of all these added chemical values by the industry. And then we have a work package 7, the demonstration in industrial relevant context. It's one of the most impactful results of the project. Then after my talk, Koen will give you a summary, or we will summarize all our progress on that. And finally, in BP8, we have analyzed, or we have studied the social, we perform a socio-economic evaluation of environmental sustainability of all the processes that we have been investigating during the project. The work package 9 is focused in dissemination, communication, exploitation, and working public and increased public acceptance of these technologies. The event that we are performing, this event is an example of the communication activities that we have been organizing during this last 4 years. This is a scheme of the project. So we are starting from the CO2 that is emitted by different kinds of industries, iron and steel, cement, and electrical power industries. We have characterized this, the emissions in CO2, the CO2 rich gases, and work in several strategies for increase the solubilization of CO2, but also other gases, as you will see later. Then we have work in, we have developed 4 different microbial cell factories, as I mentioned, one based on Clostridium stains for producing branched alcohols, another for coproavidos for producing plastics, bioplastics, and 2 enzymatic approaches for producing formic acid and lactic acid. Then we have demonstrated, or we wanted to demonstrate their feasibility in industrial relevant conditions, and after at the end of the project, we have also included some validations by industry partners. So here we mention the different industrial markets that we are focused in. The chemical industry for the alcohols, the chemical and plastic industry for the bioplastics, and also food and feed ingredients for formic acid and lactic acid. Here we try to summarize the expected results that we want to achieve or wanted to achieve with the project. We want to work on the assessment and validation of 3 low energy microbial processing systems, as I mentioned, aerobic and anaerobic microorganisms, and also enzymatic processes capable to converting CO2 emissions from the iron and steel industry into valuable industrial products. We expect to produce these 4 chemical building blocks from CO2, applying biotechnologies, and that building blocks have applications in food, feed, chemical, and plastic industries. We have also worked in the installation of a pilot plant in an industrial setting in order to demonstrate and validate the effectiveness of this, the most promising building blocks using CO2 from a real CO2 effluent. And finally, we are working in we have been working in improving the public perception of these technologies at social level. Which is our target audience? Well, we are focused on industry, as you will see, different kinds of industries. From one side, the ones that can be CO2 suppliers, but also the end users, the chemical, the food and feed, the plastic industries. All these kinds of industries are partners of our consortium, and also we are focused in the biotech industry that should provide technology to biotransform the CO2 in these chemicals. We are also focused in regulators, in policymakers, to the public and private investors, and also in local authorities, in decision makers, in order to try to, as I mentioned before, try to increase the implementation of these technologies in the society, and to contribute to the EU policy, CCU European policies. But we are, of course, focused also in the scientific community. We are also collaborating with other Horizon 2020 initiatives and projects. So, in fact, we will have the participation of several colleagues from other related projects in the session of science this afternoon, and also to the general public. This is a consortium. As I mentioned, we are 18 partners from 8 countries, 5 SMEs, 5 large industries, 4 research and technological organizations, and 4 universities, which are quite balanced consortium. Finally, in order to introduce the event of this half-a-day event, we have prepared 3 sessions. The first one is focused in industry. Here we will try to show the most impactful results from the industry perspective, but also some partners from some companies will give you some thoughts and about the expectations of large industries and small industries in the use of these BIOCCU strategies. This afternoon after lunch we will have one session dedicated to science, where we will show partners of the project. We will summarize the most interesting results from obtained during the project in the different stages of the different parts of the project. From one side, from CO2 celebration tech strategies, also the microbial cell factories and the downstream technologies, and also a panel discussion where other colleagues from other projects sister projects or related projects will participate in order to give an overview of the current status of these BIOCCU technologies. And finally, tomorrow we will have a session focused on the policy, where we will introduce all the results, conclusions, and thoughts about the social, economic sustainability of these kind of technologies, but also related with environmental aspects. After that, there is a trip on a boat. It's a visit to the mobile for the inauguration of the mobile pilot plant in ArcelorMittal installations. That you are all welcome, the ones that you have inscribed. So that's all from my side. Thank you again to all of you for being here, the ones that are following us from online, and I hope you enjoy very, very much this half an a day session. Thank you.
Feel free to put your questions, please, online participants, and I'll try to read them and to bring them forth once the presentations, each presentations on the industry sessions are over. So right now, the next speaker is Koen Kwartier. He's innovation manager in the Biobase Europe pilot plant and bioscience engineer, and he is, along with their colleagues, is participating mainly in developing our pilot demonstrator in the project, and he's going to speak about the bioreactor and basically the piloting in an industry relevant environment. So, Koen, whenever you want to conclude, the floor is yours.
Thank you very much.
Thank you.
Thank you for the introduction, and thank you also for the AquaTT team to organize all of this nice event. And I'm happy to see the BIOCON-CO2 partners again in real life. I will be talking today about piloting in an industrially relevant environment, piloting of gas fermentation. And the industrially relevant environment I will be talking about is the site of ArcelorMittal, steel manufacturing company, which is just a couple of kilometers north from here. Maybe first of all, let me introduce a bit our company to have an idea in which way we look at CCU. For those who don't know us, Biobase Europe Pilot Plant is a company active in the industrial biotech sector, and we actually act as an open access pilot facility. This means that we help our clients, we help our partners to scale up processes that they developed, biotech processes that they developed on a lab scale. We scale it up to 150 liter, 1,500, 15,000 liter, and soon, in 1 year, also to 75,000 liter scale. And in this way, we can help them decide whether they should continue, whether they should commercialize their biotech processes or not. So our mission statement is to enable the transition to a sustainable and bio-based economy, and we do this by developing processes from the lab and then also scale it up, as said, to 15,000 liter scale. And we also do custom manufacturing trials for certain clients. Besides working together with clients, we also work in consortium projects like BIOCON-CO2, where typically we also do mostly development work and especially scale up. So industrial biotech is all about using renewable carbon, to reduce our dependence on fossil fuels. Traditionally, we used 1G sugars, 2G sugars, biomass to produce interesting products. But in the last decades, a lot of interest is also going to the use of CO2, because also CO2 is a source of renewable carbon that can be converted by microbes to produce very valuable products. Where does this CO2 come from? We all know there is a lot of CO2. There is CO2 hanging in this room. There are also a lot of point sources of CO2. Steel manufacturing, of course, what we will be talking about today. In the BIOCON-CO2 project, we've also been looking at cement manufacturing and power plants, the so-called hard-to-abate sectors or hard-to-decarbonize sectors. And besides those sectors, there is also biogenic CO2, like CO2 coming from fermentation plants or waste gasification, and so on. So let's talk a bit about steel manufacturing. As said, we have our partner, also partner in BIOCON-CO2 project, ArcelorMittal, who unfortunately couldn't be here today. But they asked me to show their company video, or at least part of the company video, to indicate where the gases are coming from. So after this slide, we will show a little movie to see where the gases come from. So basically, steel manufacturing, we have coal that is converted into coke, which is used as a reductant to, in the blast furnace, use iron ore. In both of these unit operations, there is a release of CO2, CO, hydrogen. And then after the hot metal is produced, it goes to the basic oxygen furnace together with some scrap. 20% of the raw material that they use in the oxygen furnace is actually waste metal, waste steel. And again, in the oxygen furnace, there is a release of CO2 and CO. So pay attention to these terms in the video. We have coke oven gas, blast furnace gas, and basic oxygen furnace gas. All sources that can be used for biotechnological processes. So we're going to watch a movie now. It's 7 minutes or 8 minutes, so it's quite long. Try to keep your attention. So yeah, if possible.
A state-of-the-art, highly functional, and in many ways essential element of today's world. It's used in a wide variety of sectors, such as the automotive sector, construction, packaging, the sanitary sector, domestic audio and video appliances, and the machine construction sector. Producing steel is an activity that encompasses the whole globe. The ArcelorMittal Group is the unrivaled #1 in the global steel industry. ArcelorMittal was created from the 2006 merger between Arcelor and Mittal Steel. ArcelorMittal Ghent, the jewel in the crown of this entity, is a fully integrated steel company situated in the seaport of Ghent. ArcelorMittal Ghent manufactures flat carbon steel products with a high added value. At its 10 square kilometer site, the different steps in ArcelorMittal Ghent's production process fit in seamlessly with one another, starting from iron ore and coal, working right through to laser-welded car body parts. ArcelorMittal Ghent conducts a green policy. All environmental parameters in terms of water, waste, energy or dust come below the average values for Europe or Japan. Moreover, steel from ArcelorMittal Ghent indirectly contributes to a cleaner world. Steel is, after all, the environmentally friendly material par excellence. It's perfect for recycling and can be recovered efficiently in the form of scrap. ArcelorMittal Ghent is a maritime steel company. It enjoys direct access to the North Sea via the Ghent-Terneuzen Canal and the Western Scheldt. Each year on its 1 kilometer-long quay, some 10 million tons of raw materials are unloaded, mainly iron ore and coal, and over 1 million tons of semi-finished and finished products are loaded. ArcelorMittal Ghent's port is accessible to seagoing Panamax vessels up to 65,000 tons. Ore stacker reclaimers carefully separate the ore into piles of different grades. After reclaiming, the different iron ore qualities are transferred to the fines bedding by means of belt conveyors. On the fines bedding, the different ores, fluxes and recycled products are piled in chevron layers. In order to make an optimal blend, the fines bedding is reclaimed over its full width. Meanwhile, coal is also being prepared for the hot metal production. Coal in its basic form is not suitable for direct use in the blast furnace burden. It must therefore be converted to coke. This is achieved by heating the coal to a temperature of 1250 degrees in an oxygen-free atmosphere. During distillation, a large quantity of gas is released, which, following purification, produces coke oven gas and other valuable byproducts such as tar, sulfur, and benzene. Coke oven gas is used as an alternative to natural gas in various production departments. A mixture of iron ore fines, recycled ferriferous products, and fluxes is baked on a slowly moving strand with coke breeze and anthracite being used as fuel. This produces sinter, a porous substance forming an ideal raw material for the blast furnaces. Once in the form of sinter, the iron ore is ready for the blast furnaces. The sinter and coke are carefully weighed and poured into the blast furnace through the hoppers. Air, heated to 1250 degrees, is blasted into the tuyere. This converts the coke and pulverized coal into a reduction gas, carbon monoxide, that can remove the oxygen from the iron ore. At the same time, this process generates the heat necessary for melting the ore. The conversion from ore into hot metal takes place as the blast furnace burden is coming down. The liquid and carbon-rich hot metal is collected in the heart of the blast furnace, where it's tapped and runs into torpedo ladles. A layer of slag is floating on top of the hot metal. This slag contains the impurities and the gangue present in the ore. The slag is tapped off, granulated in a powerful water jet, dewatered in drum filters, and transported to the customers of the cement industry. During the production of hot metal, gas is generated containing a certain amount of dust from the blast furnace burden. This gas is purified and conveyed to various consumers, the main one being the power plant of Electrabel.
That you will also see tomorrow if you do the boat visit, you will see it. Nowadays this is not happening anymore because they use part of the CO that they produce, they use it internally for energy production. So you will see also tomorrow, I will also show you that there is a very big pipeline now that is laying in the harbor of Ghent, but it is not in use anymore, or not a lot. Unless they have a real overproduction of gases that they cannot use themselves, then they send it to the power plant to be valorized. And then the gases that are less energetically, less high in energy, these can be used for the biological processes. So I hope this gave you a bit of, I had a slide for the movie, a bit of an introduction of how the steel making works. I stopped now where the hot metal is produced. Normally then it also goes to a basic oxygen furnace where oxygen is inserted and impurities are removed. But that would take too long for the movie, and I have to do some talking still, so let's continue. All of these gases can be used for CCU, carbon capture and utilization. CO2 can be used directly in carbonated rings, greenhouses, but what we target is a conversion. Can be done chemically, but we will be talking about biological CCU. That's what BIOCON-CO2 is about. Biological CCU has a couple of advantages compared to chemical CCU. The microbes are more tolerant to impurities. Processes are running at ambient pressures and temperatures. Product specificity is high, and we can create a very wide variety of products. But the technology readiness level is up to now quite low, depending, of course, on which process, which product you are targeting. So that's again where projects as BIOCON-CO2 are very valuable. We will talk about the science and the microbial cell factories in the next session, where we developed microbial cell factories on low TRL levels in the lab. Within BIOCON-CO2 and what Bio-based Europe pilot plant has been targeting is how do we cover the next step? How do we go from the lab scale to the industrial scale to the pre-commercial scale? So how do we bridge the value of that for carbon capture and utilization? There are a couple of ways to do that. I listed some contaminants that are present in the gas. These are impurities that might be toxic to the microbes. You could take these contaminants and use them in your lab. I show some pictures of our bioreactors. We could perfectly take some of these contaminants and supplement them to our cultivation media or add them to a synthetic gas mixture. Or we could even compress the gas at the site of the emitter and bring it to our lab. From experience, we've noticed that this is not always very easy and it requires quite expensive equipment. Though all of these strategies can give you a very good indication of early on in the project whether contaminants are toxic to your microbes. But to really demonstrate it on a real scale, with a real industrial gas, and to really validate the processes within BIOCON-CO2, we are bringing the plant to the emission source. So what you see here is a containerized biotech lab that we designed and constructed together with MTSA Technopower, who was our partner in designing and constructing this equipment. MTSA Technopower is a company that is specialized in custom manufacturing chemical, pharmaceutical, biotech solutions for their clients. So we had a very nice partnership with them, and I'm happy to say, and you might have seen it on LinkedIn, that our pilot is now almost ready for operation. And as said, this is the most reliable approach to validate gas fermentation process and go from, and bring these technologies out of the lab, basically. So maybe some metrics. It doesn't look like it on the picture, but it's 14 meters long, so it's quite big. You will see tomorrow if you're joining, hopefully. We will use it to scale up gas fermentation, to validate it to validate processes in industrial conditions. It's completely standalone, so it has everything required to do biotech processes. The only thing we need from the CO2 emitter is the gas, of course, and power supply. That's it. For the rest, it has its own steam generator for sterilization purposes. It has a chiller to cool down the reactors. It even has a built-in hydrogen generator. In case there is not enough energy present in the industrial gas, we can supplement it with additional hydrogen. It's not green hydrogen, but if we go to the next scale, it should be green hydrogen, of course. It contains 3 fermenter vessels, and we can connect 2 different industrial gas feeds to really make mixes for our microbes. And the pressures that we can use can go up to 8 bar G to cope with mass transfer limitations that are typically a challenge in bio-CCU processes. So tomorrow we will visit the plant. Hopefully you can all join. If not, really consider to join because it's going to be very interesting. I added some pictures here from the process of installing it at ArcelorMittal. On the left-hand side, what you see there is the first step of putting the foundation. Before, it was kind of a forest. It was quite difficult to get it all removed, to get the permits to do so. But ArcelorMittal, when the pilot is gone, after a couple of years, they will have to replant the trees again, so that's good. So on the left-hand side, you see some civil works. In the middle, that is the installation of the piping. You see on the top of the pictures, the big piping that carries the gas. The blue support that you see supports the smaller pipings because we, of course, only use a slipstream of what they emit. And tomorrow you will see that they are connected on top to the big piping. Then on the right-hand side, you see the arrival of the pilot. It was constructed in the Netherlands at the company MTSA. When it was finished, put on a truck, and it arrived at ArcelorMittal a couple of weeks ago. And on the right-hand side, you see the installation of the pilot. Right now, we are in the process of commissioning it. We need to get the green light from all the safety departments at ArcelorMittal, which is quite a struggle, but we're managing. Then we will start up the commissioning together with our partner MTSA, and then if everything goes well, next week we can actually start our first fermentation processes with the real gas of ArcelorMittal. So it's quite an exciting time. That was it for now. If you want to know more about it, of course, you can talk to me. You can also talk to Jan ten Have, our partner from MTSA. And tomorrow, during the site visit, there is, of course, also time to ask some more questions. So that was it. I hope I stayed within the time.
Thank you very much. Okay, I don't know if from our face-to-face audience, if there is any question to be addressed to Con. Yes, Aline?
So you talked about your hydrogen unit. Is it like an electrolysis unit or what kind
It's an electrolyzer unit, yeah, indeed. That's correct. Yeah.
So you're producing hydrogen and carbon monoxide with it, or do you have a hydrogen separator as well?
It's hydrogen and oxygen. So it's a water electrolyzer, so we make hydrogen and oxygen as byproduct, but that is just released. And then the hydrogen is mixed together with the industrial gas that we get. That's how we'll do it.
You can go ahead, Anna.
Which kind of fermentations can you run in these facilities? Aerobic, anaerobic?
That's a good question, and we designed it very flexibly. That's how we do everything at Bio-based Europe pilot plant. All our equipment, fermentation and downstream processing has to suit different needs. It will not be optimal for one process, but it should suit everything. And also for this pilot, we decided to design it in a way that we can do gas fermentation, but also do aerobic fermentations. We could perfectly ferment with yeasts and E. coli. So yeah, it's very flexible in that respect.
Gabriela, please.
Many questions.
Yes.
It will be Cupria virus incator. That will be the first one, yeah. We have tested the Cupria virus incator strain in the lab with a synthetic mix without any contaminants. And it worked. And we know that we will be able to get quite some good titers, let's hope. So yeah, the Cupria virus incator will be the first microorganism of choice. Okay.
What kind of reactors are you using? I mean, this gas fermentation are quite special, so like loop reactors, but how do they fit in such a container?
Yeah, it's not a loop reactor. It's not a bubble column. It's just a standard CSTR. CSTRs are flexible. That's again the reason why we chose to go for CSTRs. They are very convenient to perform. Yeah, for R&D purposes, so to speak. Probably not, because the power consumption would become too high. It's a very good point, but we specifically chose for CSTRs because, again, for R&D purposes, the idea of this pilot is really to validate whether the biotech process works with the real industrial gas. Then for scale-up, in the next stage, probably we would have to look for other designs.
Instrumentation is the last water transfer, and how do you want to simulate that with this kind of reactor?
Yeah, we have chosen to be able to operate it at 8 bar, so under elevated pressures, and elevated pressures should help us to kind of cope with the mass transfer limitations.
But if you scale up, you have really different gas volumes, which you probably cannot pressurize.
Yeah.
20 bars.
Yeah, that's correct. That's a good point. But it's a choice that you have to make. Again, for this process, we choose for CSTRs because they are flexible. We're very used to working with them. To go to the next step, indeed. But at least we will have shown that the industrial gas works for the microbes that we will use, or doesn't, of course. Yeah. Let's hope it works.
How long will the campaign last until validation? What do you understand by validation is then to reach a certain yield, or what would be then?
Yeah, probably indeed. We will get an idea based on the growth rate of the microbe, based on the titer that they reach, the product that we aim for, and the productivity. These are the 3 metrics that we will look at. Probably everything will go a bit slower. Let's hope it's just that, and they don't die immediately because of the contaminants. But indeed, these are typical metrics: probably productivity and the titer, the final titers.
But how long do you expect that will last? Is there a plan?
We hope to finish it within the BIOCON-CO2 project, which is, of course, which is difficult. We will still be able to do a run in the BIOCON-CO2 project. The fermentation trial lasts for, let's say, a week, maybe a bit longer. The pilot will stay at ArcelorMittal until the end of this year. So we will continue to perform trials at their site. And then I didn't mention it during the presentation. We partner within another consortium-based project, and the pilot will move to Finland to be connected to a gasification plant. And then the process starts again.
Okay, sorry.
Yeah.
I think we need to move on. Thank you very much, Gun. I get another question, but I think I'll save it for the panel session.
We have 2 days.
So now we need to move on because we have waiting online. We have Jean-Luc Dubois, it's technical director in Arkema, scientific director, sorry. And she's coordinating research activities in this important company. So hello, Jean-Luc. I think we saw you on the screen. I don't know if you can hear us.
Yes, and you?
Quite low. I don't know if we can turn the volume a little bit on. Yes. But we can hear you quite clearly, Jean-Luc.
Okay, good.
Perfect now.
And I share my screen.
Yeah.
Full screen. Is it okay?
Yeah.
Do you see it?
Not yet. Just a moment, Jean-Luc. We'll try to fix it. Now we can see your screen. Yes. So whenever you want, the floor is yours then, Jean-Luc. Great.
Thank you very much, and I'm sorry I'm not able to attend physically this time, but I will present some economics analysis that we have done in the course of the project, with a special focus on products which are polyhydroxyalkanoates. These are polymeric materials made by microorganisms. Okay, now I need. Okay, first a slide to illustrate the product selection that we did at the beginning of the project, or when doing the application for the proposal. Here you see on this slide many different type of products and 2 different scales. So a first scale is basically the heat of combustion of the product on the left side, and on the right side is an estimate of the value creation per ton of CO2 that would be consumed. the heat of combustion is basically the image of the energy which would be needed to make the conversion of CO2 to a product. So it's easily accessible, let's say, in terms of value from handbook database, let's say. For the value creation, in this case, is the value of the product divided by the amount of CO2 that would be consumed. So on that scale, you see on the left side the product that do not need a lot of energy to be converted, and these are basically the products which are already on the market, like urea or carbonates or salicylic acid, which are available already today. And then in terms of value creation, it's not a big value creation on CO2 basis for those, but it does not require that much energy. And then on the right side, we have products which are consuming a lot of energy to be made from CO2, and unfortunately, they do not generate that much value from CO2, so that means it's going to be challenging, even though they have big markets. Yeah? And then in the central part, there are plenty of opportunities. Some of them have been investigated within the BIOCON-CO2 project, like formic acid. So there are the green ones, yeah. Formic acid, lactic acid. Some product could be investigated, like diols, alcohols, or other alcohols. And some other products have not yet been investigated, but would deserve to have some attention. So before the start of the project, we first made a selection, and you see in the central part, maybe I have should have the laser pointer. Yes. In the central part, you see PHA, different type of PHA materials, which are, let's say, right in the middle, consume energy, but offer a reasonable value creation. So that's why those products were included. What also changed during the BIOCON-CO2 project is the value of the CO2 emission credits. For a long time, the CO2 value has been very low, below 20 euro per ton of CO2. But recently, what we have seen is that the value increased to about 80 euro per ton since the end of last year, and is expected to remain at a fairly high value. Yeah. Some other work for identifying product of interest. So what I show here, because it's quite often a comment that I hear, is that we don't have easily access to market value of products, but some data are available from let's say trades, from customs, because people have to pay import tax in many countries. So trades of important chemicals are freely available, and it's possible, and this is what I did here, is to plot the imported unit value, so the value per ton of product versus the amount traded and imported in different countries. So the first figure is for methanol, and what I indicate here is the largest importer. So for 2021, the imported value was around $400 per ton. But what is relevant in this case is to see, okay, these are the big volumes, but what you see is when the volumes is decreasing, of course, the imported value is also increasing. Yeah? For acetone, we have a similar trend. You have big volumes, low price, I would say, But for lower volume, you can already see it can increase the cost for importing by 50%. Easily. So what is important to identify for the product we want to make is what is exactly the scale at which we want to build a plant and in which country, which location this would be done. Of course, if it's to build a plant in regions where there is already a low price, it's not as attractive probably than in a region where people have to pay a higher price to have access to the same chemicals. So here data for acetone and other products. So ethylene glycol is also an interesting product with, let's say, again, somewhere around 30 to 50% higher price for production scale, which is between 1,000 and 10,000 tons per year capacity. For itaconic acid, I showed the data from another source of information. In fact, this is coming from Indian customs because data are available in the period of 2013 to 2016. And this period is important because the crude oil price varied between $100 per barrel down to $40 per barrel during this period. So at the same time, we can have a kind of correlation, and in special case, very low correlation between the price of crude oil and the price of itaconic acid, which is a diacid currently produced by fermentation also, but for fermentation of sugars. So that product could be also attractive, but the value is currently not that high. Based on those data, I will spend some time to explain this figure. Another way to identify which product is of interest is try to allocate the value creation only to hydrogen. Yeah. So what it means here is that the value of the product is allocated only to the cost, the purchase cost of hydrogen that would be needed to make the product. That means that all the other costs are either considered as being zero or covered by the CO2 emission credit that we have to pay for the product. Yeah. So that way, on this graph also, what I show is a range. So the blue bar here is more or less the cost for fossil hydrogen today, which is also basically the expected long-term cost for hydrogen, renewable hydrogen made by electrolysis in the future. Yeah? And the green bar is more the cost of renewable hydrogen today. So that means somewhere between 4,000 and 8,000 US dollar per ton of hydrogen, something like that for renewable hydrogen today. Yeah? And let's take the case of formic acid. So formic acid, I have a range, yeah, based on the imported value that we have seen, reasonable imported value. So that means in the case of formic acid, we are well above the cost of renewable hydrogen today, of course, well above the long-term price for renewable hydrogen in the future. So formic acid, oxalic acid are today products that deserve some interest for conversion. For lactic acid, it's a little bit more challenging on a short-term basis because of the, let's say, the cost for hydrogen is really too close, yeah, from the renewable hydrogen today. Some other products like methanol, ethanol, and acetone will be interesting on long-term basis, but on short-term basis, probably not the best target. And on this graph, what you can see is the PHA, so the polyhydroxyalkanoate, which are rather high, assuming a price market value on average for PHA around $4,000 per ton, because this is the long-term target for PHA polymers produced today by fermentation of sugar or fatty acids. Yeah. So this is an attractive target. And a special note is the value, which is beside the chemical. So 1 or 0.5 here is a ratio of hydrogen to CO2. So for PHA, what we see is that we need to consume more hydrogen per mole of CO2 compared to oxalic or formic acid. So it's one of the very few products with high hydrogen to CO2 ratio, which is still attractive. So PHA deserves some interest. Another important point is that we had to document is what are currently the cost of industrial plants for gas fermenters. And there are basically 4 main technologies which have been developed in different fields. In the past, Ineos Bio had a gas fermenter in the US in Florida for CO hydrogen fermentation to ethanol. Calista as a gas fermenter for methane conversion to proteins being implemented. Of course, Lanzatech and ArcelorMittal have a conversion of still gas to ethanol, and Unibio has also a plant for methane conversion to protein. So there are different type of technologies, and we collected from press release and so on. We collected some data on those plants. It's important to show to company management that this technology exists at large scale and are not only some dreams of the laboratory. So what is important to identify is capital cost. Because that's typically a new type of technology, so that's a area where we don't have enough information to guess what would be the production cost and so on. But based on all those data, even though we have different type of technologies, what we can see is this kind of process cost about somewhere between $3,000 and $6,000 per ton in capex. I should add these data were before the COVID crisis, but that gives us a first basis for an estimate of cost. So to make the economic evaluation of PHA production, I used a Monte Carlo simulation model, which means that instead of doing only an evaluation for one set of economic data, so that means cost of raw materials and only one investment cost and so on. I used several thousands of simulation and look at the statistical results. Yeah. So first, we had to choose a plant scale, and in this case, I choose 100,000 tons. It's rather large plant. But you will see at the end that this kind of scale, more or less, will be needed to have attractive economics. So first thing, we need to create a mass balance
based on the data that we have from the fermentation. We can derive a ratio of CO2 hydrogen which is needed. Processed water, in this case, the value may be low, but we estimate that we would recirculate a lot of water in the process, and it's not the key parameter, as you will see afterwards. And we need to feed, let's say, the microbes with some nutrients. So these are the raw materials that we need. Then we have two products. We have the PHA on one side, and in fact, the microbe, they are going to accumulate the polymer in their cell. And so we are going to have a co-product, which will be the cellular biomass. It's going to be significant, even if we assume here that more or less we have 80% of the weight, the final weight of the microbe, which is the PHA. And of course, we have wastewater, same amount than what we consume. Based on that and using typical data or typical models, we know that we will have 7 process steps. That the process will be used in a batch mode because we need to accumulate the PHA in the microbe. We have 3,000 simulations, and what we need also in this case is we need some energy for the process, and so we add on the raw material cost, we add 15% of the cost for the energy. So these are the basis, and from those basic data that we estimate that the capital cost, so ISBL and inside and outside battery limits, would have a probability at 50% probability to be around 400 million. So it's a significant number. We need to add on top of that some working capital to be able to start the plant, and also a startup cost. There are some equipment that we know will have to be replaced. It's typical value for this kind of process, and we need to get a grant, a significant grant. In this case, 100 million euro of US dollar. Everything is in US dollar in this case to start. So at the end, we need this amount of money. And basically, because it's 3,000 simulation, we have 3,000 different cases which are behind that. Then we need to do the same thing for all raw materials and products. So I will not detail everything, but for each one of them, we looked at market data for the raw materials for the product. We assigned a distribution for each one of them. And typically for hydrogen, so we took current fossil-based hydrogen, which is also the long-term price for renewable hydrogen. So hydrogen is somewhere between 1,600 and 2,400 US dollar per ton. And for the PHA, we just assume that it would have a market price, attractive market price, which is where we hope the current PHA would reach from sugar fermentation. We have also some biomass which is co-produced, and in this case, we just assumed it would have a value like fertilizer, because we don't really have a better alternative today. Fertilizer, because the biomass will be rich in nitrogen and other oligoelements. And we have some wastewater that we have to take into account. The next step was to derive a correlation matrix, because those prices, they can be either independent, but for some of them, they have to vary simultaneously and either in the same direction or in the opposite direction. So for each one of them, we created a correlation. We created a correlation matrix, which is used in the Monte Carlo simulation. And finally, the main results for deciding whether the case is attractive. So here on the top left, what we show is a net present value after 10 years of production. So that means it's the accumulated money that we make on the process. And what is attractive for the management is to see that here the probability of losing money after 10 years of operation is quite low. Yeah, so it's a first sign that the project is attractive. The second important figure is this one, which is the cumulative net present value over time. So initially we invest money in building a plant, so that's where we take a risk. So that's the image of the risk that we have to take. Yeah? We have to invest 400 million, and then we start to produce and so to make money. And what we see here is that after 4 years, we cover the investment cost. Yeah, so the payback time is rather short, so it makes a project attractive. And after we, of course, we continue to make money. And what is important, not shown on this figure, is that since we make money, we pay taxes. And with the taxes that we have to pay, a profit tax, yeah, the subsidies, even it was significant at the beginning, would have been repaid within 3 years. This other figure here is still the net present value versus time, but for different internal rate of return. So what we calculate is what is the rate of return which is necessary to have a zero net present value after 10 years, and the value is 37%. So this is another indicator which is used by some companies or some management to decide if the project is attractive enough. And in the present case, 37% is a typical rate that would be sufficient for a project that would be classified as a high-risk project. Yeah. So, and typically, since CO2 conversion by microbes would be a completely new technology, it is a high-risk project. So, this indicator shows that this case is attractive enough. Then, what we can also derive from that is the cost structure. Try to see what weighs a lot in the production cost. So of course we have to buy some CO2. In this case, I just assume we purchase CO2 at about 50 euro per ton, yeah, which is a cost to get it clean enough to be able to use it. Yeah? Then, of course, hydrogen as a big contributor to the production cost. Then, as I mentioned before, processed water is not so important. The other nutrients are not so important either in the cost structure. We have some other utilities, but we also have some other variable costs. And typically here in the variable cost, we have to pay some royalties because we use technologies from partners. We have some distribution and sales costs. We have R&D. So there are some variable costs. The labor cost is not so important in this case because we have a very big plant. Even though we have 35 operators to operate that plant, in the total labor cost is not so important in the project. It would not be the prime target, let's say, to reduce the cost of production. We have a lot of other fixed costs. We have to integrate some maintenance, property tax, some insurance, and so on. So these are taken care here. We have the depreciation for the large capex that we have, and luckily, I would say, we pay tax. And we pay tax because we make a profit. So the tax are important in this system. I took 30% of tax for the production, and we create value from our co-products. So the fertilizer in this case, which is the biomass. Of course, if we could sell the biomass for a better application, it would help to bring the cost of production down. Yeah? So we have a cost of production which appears here. Other indicators that are important derived from all this statistical work is what is the minimum price at which we need to sell the polymer, and typically here it's what is the value at which we get a zero value after 10 years, and that means we can already say that the PHA has to be above $2,000. So this could be used as a methodology even for other products than PHA. We could use the same method to determine a minimum price at which we have to sell and to eliminate some products that will never be able to reach attractive value. Also from this distribution, what also is important for management is sometimes is what is the probability to have a production cost before depreciation and tax. What is the probability to have a production cost below, let's say, $1,700? And here what we can say from the distribution of the 3,000 cases is that there is 95% probability to be below $1,700 per ton. So these are sometimes people prefer to look at that criteria to decide if the case is attractive. And the last figure is what I call a tornado graph, which is used to show which parameter, which has each one of them have uncertainty. They have a distribution of value, which distribution has the highest impact on the net present value, so the final economics that we want to look at. And in fact, it shows that the first parameter is the capex. We have a lot of uncertainty on the cost of the plant. Of course, we are at very preliminary design. We don't have information. The pilot even didn't start on that, so we have a lot of uncertainty on the capex, and we see what impact it has on the final result. But the second parameter, which has a lot of impact, is the sales price of the product. Even though we say it's somewhere between 3,700 and 5,000 something, the distribution is very large and has a very strong impact on the final result. So these are the two parameters that we would need to improve in terms of distribution as soon as possible to make the case more precise. So, as a conclusion, with the methodology I described here, we can list some products which are attractive. Preferably, they have a low hydrogen to CO2 ratio. They have a low combustion energy. Their market value strongly depend on the location and let's say the competition with imported products. So it might be wise to identify countries and location where competition is also at higher price. The PHAs in general are the products which are among the promising targets, but what we still need to improve are technologies for improving the hydrogen dissolution and heat management. I didn't have time to discuss that here, but these are two key parameters in the fermentation which are going to affect the capex significantly, and to define the appropriate plant size and the location for this kind of products. Well, thank you for your attention.
Thank you, sir. Thank you so much, Jean-Luc, for your presentation. I don't know if from the audience here if there is any question. No? From the online note, I may ask you some general questions, Jean-Luc, from the simulations that you've run and everything after all the results that we've been so far. It just sets a guess. So more or less, what is the range you expect that a private investor can expect on the return of their investment? We've seen some MPVs results and that, but more or less in which range of percentages we're talking about if we expect a shareholder, an important shareholder, to invest in a PHE and in eventual PHA industrial project, more or less.
Well, it strongly depends on what the investors, let's say, have done before. And that's why I use several different criteria to analyze the cases. Some people will say this is very risky, so I focus on this. I need to. Sorry, just 1 second. I want the laser pointer again. Okay, I want this criteria. So the discounted cash flow rate of return. I want a high ratio, for that. Because I had previous project and I know this is my selection criteria. So that means they can accept to take a lot of risk, take a high risk project, but they want to make a lot of money very quickly. It's more or less the same, to compensate for the risks that they have to take. And some other people will focus on the payback time. Because, you invest a lot of money, you want a very fast return. But in this case, it's probably because they know the market can change very quickly. And if you have a short payback time, it means that, you have a clear view on what could happen in the next 5-10 years, but not so much afterwards. So the shorter your payback time, the better it is. After 4 years here, you have paid your capex. You repaid your capex. So from there, I would say, if the market changes drastically, you can stop losing money if you stop the plant. So some people would focus on that because of that reason. And this curve is also because people can accept various things, and what they want is to find a case where they are sure they are not going to lose money after 10 years, so they would prefer to focus on that. So it really depends how the investor or the company has been looking at project in the past, and they use different criteria.
Okay, thank you, Jean-Luc. It's indeed a high number, and it's moving numbers, and typically from maybe the pharma industry and also biotech industry, which there is high risk, and of course shareholders expect higher return.
It's exactly the same set of data, only looking at those data with different angles.
Yes. Thank you, Jean-Luc. There is a question from Anna, and then from Andreas, and then we'll stop because we're quite ahead of time. Yes, of course.
When there is a question from the room, I cannot hear the question, so if you can repeat the question afterwards.
Of course. We just put some microphones here. Let me know if you can hear, because and just can speak a little bit louder.
Hi, Jean-Luc. Can you hear me?
Hello. Yes.
Hi. Okay, I have a question because you have done these calculations. Which is the CO2 source that you considered? I mean, do you have to buy pure CO2, or you are using some CO2 from some company in the neighborhood?
In this case, I just assume that we buy CO2, which is more or less the value which is estimated for carbon capture and storage. Because anyway, when you have to store the CO2, you have anyway some cleaning, compression, and so on. So it's not CO2 for free. It's not at negative value either. It's with a small cost, which would be equivalent for storage.
Then Andreas, and then we'll just leave for the next. Thank you for coming forth.
Hello, Jean-Luc.
Hello.
You hear me? Okay. Yeah, just a question. I don't know if you can or want to answer it, but now when we look at this looks very promising from a large scale. I mean, maybe a bit further down the road in the future. And PHA production is now simulated on a small scale at ArcelorMittal with a mobile pilot reactor. Are you already thinking bigger beyond that? Is this just a general study, or are there any plans for upscaling?
The problem will be, the first problem will be how small could be a plant and still be economically attractive. Here, it's a simulation is for 100,000 tons. If, let's say, I divide the plant by factor of 10,000 tons only, that means, and maybe I can show from here, that means that the depreciation part and the other fixed cost part in the cost of production would be, to make it simple, would double. Yeah. So it's important, but probably if we can keep a good price for the PHA, it's still attractive. Now, if we have to go to even smaller scale, that's going to be more and more difficult. Yeah. So the similar work than what we did would have to be done for a different plant scale. And then the integration on the site would have to be looked at in order to minimize some costs.
Okay, I think there are no further questions. I'll just check if the online participants have some question in the chat, but I think not. Okay, then.
Thank you.
Thanks so much for coming, Jean-Luc. Your presentation has been very nice, interesting from this point of view. And so right now, as on the schedule, we have a short coffee break. We'll come back, I think, at 11:10 with the next presentation. So thank you so much for the attention, and we'll come back a little bit soon. Thank you. So Jim, he's project engineer at ENGIE Laborelec. He's leading projects in carbon capture and utilization and storage. And he will be now presenting a speech on industrial perspective on how CO2 emissions can be valorized. So Jim, when you can share your screen, and whenever you feel ready, the floor is yours. Thank you.
Okay, thanks a lot for the introduction. Okay, can you confirm that you see my screen well?
Yes.
Is that the right one? Okay, this should be good.
It's perfect now, thank you.
Okay, so good morning everyone. So today I'll be talking about carbon capture and utilization within ENGIE. But before that, I would like to thank the organization for giving me the chance to present here and to have our take on what CCU is. So, CCU at ENGIE. Before talking about CCU, I need indeed to do a small introduction of who we are at ENGIE, and more precisely at ENGIE Laborelec, where I am working. So ENGIE is a globally present energy utility that has the ambition to lead the energy transition. And among other things, we are producers of electricity. Globally speaking, we have a capacity of close to 100 gigawatts of production. About a third of that is renewable, and that means that we are able to produce over 400 terawatt hours of electricity per year. Being in a very moving field, we are always on the outlook of how technologically speaking and business speaking the sector is evolving. So that means that at ENGIE we are investing in renewable in research and development. We have a roadmap which is close to 140 million euro of spending per year, and that employs close to 500 researchers worldwide. And in parallel to that, we have also a corporate venture arm which aims to invest in emerging startups and projects. Globally speaking, we are around 100,000 employees worldwide, but as you can see on the map, mainly centered on Europe and more precisely on France. Indeed, ENGIE is a large industrial French player. Within that big entity, indeed, we have smaller ones, and there I belong in ENGIE Laborelec, which is a leading expertise and research center. So we are part of these 500 researchers worldwide, and we are mostly focusing on the electrical power technologies, with indeed a strong focus on the energy transition and net zero carbon. At Laborelec, we are headquartered in Belgium, but we also have a presence elsewhere in Europe, in France, Netherlands, and Germany, but also a bit further out in Chile and in the Middle East. And what we do is basically we combine the knowledge of highly skilled experts that we have in Laborelec. I have the chance of having over 300 colleagues which are highly skilled in Laborelec on different topics. We combine that knowledge with operational experience, because we often go to existing assets of ENGIE, but also of external customers. And we combine that knowledge with state-of-the-art analysis and measurement capabilities that we hold in our labs in Linkebeek. And we do all this to offer operational R&D. So you will have noticed in the choice of words here that we are more focusing on higher TRL technologies. And we offer also, alongside that, specialized expertise, and in order to propose tailor-made global solutions. So enough for the presentation. I don't want to bore you too much out. So before diving into a few projects that we have on CCU at ENGIE, I would like to remind a bit what the basics for CCU are for us and why we think it makes sense in the roadmap towards net zero in the future. So, starting this reflection, I think it's important to remind that defossilizing power generation is not enough, indeed, to reach net zero. This is a global thing that tends to be accepted now. IEA says it, IPCC says it, so it's not only ENGIE, indeed. And for the good reason that electricity utilization is only part of the final energy mix that is utilized worldwide. We also use fossil fuels directly for other applications. So how do we get to net zero? Indeed, we have a roadmap that goes into different actions. And the first is to try to reduce the energy that we use through the leverage of energy efficiency measures. The second aspect that needs to be followed, and in that here the order of appearance of the different levers is important. So first, the energy efficiency. Second is to increase the mix, increase the share of electricity used in the final energy mix through direct electrification wherever we can, because indeed this is the most efficient, energy efficient way of using electricity for the same kind of values that we are doing today. So indeed the electric car is a good example of that. And when for sectors and for CO2 emissions where these two levers are inefficient, we need to look into sector coupling. So that means coupling molecules and electricity, and this is enabled by power to molecules indeed. And this will be necessary for the so-called hard-to-abate sectors, mainly two of them, the heavy transport, where we are indeed thinking directly about aviation, but also the maritime sector, where we have a need for energy-dense fuels, energy-dense molecules for autonomy reasons, and thus that needs to be fuels that cannot be electrified directly. But also the second sector is the heavy industry, where we have industries that have CO2 emissions that are linked to the process itself, and as such electrifying it will not avoid all the emissions which are linked to this industry, but also industries where we have needs for high temperature heat, which is very hard to electrify today. So for these sectors, we will need molecules. And indeed, the first that comes to mind when we are thinking about these molecules, which is high on the agenda in the media and so on, is low carbon hydrogen. Indeed, it can be produced using renewable or low carbon electricity, using an electrolyzer and water as an input to produce hydrogen and oxygen alongside it. It can be a solution, but we know that hydrogen is complicated to use in these sectors for several reasons. The first is that hydrogen has inherently, and this is something we cannot cope with, it has a low volumetric energy density when we compare it to other fuels. So if we are to build an infrastructure, a global infrastructure that uses hydrogen, we will need oversized infrastructure to move energy around and to leverage this energy. Second, we know that hydrogen is also a molecule that is notorious for causing material degradation through embrittlement of the materials. And furthermore, hydrogen being very small molecules, it tends to creep up in any defect that you may have in your material and to leak out to the environment, which is indeed something you want to avoid. And finally, and maybe most important, hydrogen is a molecule we are not used to use today in our common life. And this is true for the midstream infrastructures, so the transmission gas grids, the distribution gas grids, anything that goes in between, but also on downstream use at the industries themselves. But you can also look at it from a personal point of view. Your cooking is not adapted to using hydrogen indeed. So if we were again to switch to a hydrogen economy, we would need to change all these infrastructures, which are already paid for, which leverage decades of R&D and which are highly adapted to what we are doing today. And indeed, we are a bit running out of time. So this is the reason why we think that starting producing hydrogen is in fact only the starter of the process chain, because we think that combining it with CO2 enables the production of molecules, methane, methanol, crude, you name it, which are molecules that have the same chemical identity than the fossil one we currently rely upon to run our processes, to move things around in the global economy that we have today. So this is why combining hydrogen with CO2 seems to be the way to go for ENGIE at least. And this combination offers a link between the renewable energy assets that we are developing heavily today with these hard to abate emissions sectors that I've been discussing, all the way recycling CO2 and enabling in the end net zero carbon cycles. So this is the reflection that started the development of CCU for ENGIE. And talking about this, I would like to introduce a few iconic CCU projects that we are currently developing at ENGIE, starting with maybe the common aspects of this project, and then I will highlight some differences that we have. There are a handful of projects that ENGIE is developing. Here are the three main ones, I think, and that I would like to discuss here. You can already see that they are all based in a neighborhood in Western Europe, in Belgium, in France, and in the Netherlands. In this representation, I have tried to a bit come up with the basic bricks of the CCU value chain, process chain. So we have always an electrolyzer in yellow. We have always a CO2 source in blue, and we have a conversion reactor here in whatever that color is. So when we look at these different projects, what we can very quickly see is that ENGIE always positions as the owner and operator of the electrolyzer, a large-scale electrolyzer. We are talking about multi-dozens, even multi-hundreds of megawatts, so very large ones. And further to that, ENGIE wants positions as an integrator of the process, because also, well, alongside these three main bricks, we also have the need for integration between these. We have the need for utilities, for water purification, for gas treatments, for electrical infrastructure, and so on. So ENGIE wants to capture that part of the projects too. So these projects are always developed in consortium mode because, we need these different inputs. They are also highly complex, so we need to team up with other entities in order to develop them. And you will notice that for each of these projects, ENGIE is collaborating with a heavy industry. In the case of Columbus in Belgium, we are combining our efforts with those of Carmeuse from the lime industry. In the case of Reus, we are combining with the steel industry, with ArcelorMittal. And in the case of High Netherlands, we are working with a heavy producer of base chemicals, BIOCON. So that's it for the common aspects. Now about the differences, except maybe the dimensioning, which is a bit different. What is interesting to notice here, I think, is that, ENGIE is the project developer for each of these, the project leader, though we team up with other collaborators. But you will have noticed that for each project, the end product is different. We have e-methane in the case of Columbus, e-crude in the case of Reus, and this crude can be then further refined to kerosene for the aviation sector, but also to naphtha, to diesel, and to e-methanol in the case of High Netherlands. So you can really see how ENGIE is agnostic when it comes to the e-fuel that is being produced and sees it only as an energy vector, basically. So this is a bit these few projects. You will have understood a bit what the drivers for ENGIE are through what I have already mentioned, but maybe here to anchor a bit the message. Why is ENGIE developing these? Well, the first and foremost point is that producing this kind of project enables ENGIE to help the decarbonization of its clients through energy-linked services and through the leverage also of our own kind of business. So this is indeed the second point, that we, through the production of these projects, we leverage existing assets, because in fact all of these projects, all the electrolyzers in these projects will be located on an existing power plant of ENGIE, thereby leveraging existing infrastructures that can be mutualized. For example, the electrical lines. Indeed, these electrolyzers are very big, so they will draw a lot of electricity, which means that we have to have a very strong electrical infrastructure, and having these already existing on the power plant is an edge for ENGIE. It is also something that is important for ENGIE because these power plants, with the increased penetration of renewable energy, are deemed to have a lower operation hours each year. And so this is a way to really utilize this kind of assets and to avoid stranding them. So this is the second driver. And the third one is that, again, this electrolyzer will draw a lot of electricity. It needs to be renewable. So it is also a way for ENGIE to leverage and to sell a lot of renewable electricity that, again, can be produced by ENGIE entities. So you will have understood that we are developing large-scale projects, but you may wonder, okay, well, they are all thermocatalytic based. We are looking at thermocatalytic methanation. Phytotropes indeed leverages metal catalyst, and also the same for methanol. And so you may wonder, well, where is BioCCU in there? It's not currently there, though we feel that it's not that we are not interested in BioCCU. And thereby I would like to have a quick comparison on what is our position on BioCCU versus thermocatalytic CCU on the next slide. And this will be my last slide, and I think that it will be interesting to kick off the discussions of the panel afterwards. So here is a bit in the main lines, what are the advantages that we see for biocatalytic CCU and thermocatalytic CCU. The first, and maybe the most important one, is on process flexibility. And this can be broken down in two aspects mainly. The flexibility that BioCCU can have on impurities is indeed an advantage for it, because when we look at these CO2 sources, steel mills, lime kilns, you have lots of impurities that are embedded in the gas matrix from where we need to source the CO2. And for thermocatalytic systems, we have these metallic catalysts which are highly sensitive to poisons, which can be sulfur, chlorine, oxygen. On the contrary, biocatalytic systems, though they have their limits, seems to be more resistant to poison. And so this can be a way to save on the CO2 treatment and thus on the costs and on the infrastructures which are linked to it. Second important aspect is that theoretically, biocatalytic system seems to be more able to adapt its load, so to reduce its load at some moments and to increase it back at others. And this is very important when we look at hydrogen-based CCU, because hydrogen needs renewable energy to be produced. Renewable energy is fluctuating depending on the weather, and being able to follow the as produced load of electricity is very important to decrease the cost of the hydrogen. Basically, when we look at base load production versus flexible load production, we have a difference of 20 to 30% in the cost of electricity, which is directly impacting the cost of the end product. So having a system that is able to follow this load is key to decrease the cost of the end product. Talking about end product, biocatalytic, leveraging these amazing enzymes that the bugs have in the system, is very interesting on a selectivity point of view in order to produce high value molecules, because you will have noticed that presenting the project that we have at ENGIE, we are producing commodities, we are producing fuels, which is very hard to compete with the fossil fuels. So we have producing higher value molecules could be a way to increase the margins and to make these projects more economically viable indeed. Though BioCCU also comes with drawbacks, and these are mainly footprint and maturity. Indeed, when we are talking footprint, we know, and I think this has been discussed extensively in the framework of BIOCON, that having to work with a liquid phase system means that we have this solubility-induced mass transfer limitation of the gases, and that means that for the same amount of gases to be transformed into the end product means that we will have larger infrastructure and thus more impact on the footprint, but also on the related capexes indeed than for thermocatalytic CCU. And finally, and maybe this is the most important drawback of BioCCU, is that we are not on the same level of maturity. Even if we do see some actors reaching interesting development, and I'm here to be blunt, thinking about Electrokia and Zatec, this is still limited. panorama. When a project developer is developing a project, you cannot have a competition between these kind of guys because there are just not many enough. And so this is something, though it's also emerging for the thermocatalytic CCU, there is already a handful of different project developers which have already operated assets and demonstration projects for some time, and so which are stronger on their development pathways to reach the kind of large-scale projects that we are developing today. And so with that, I would like to thank you for your attention, and I'll be happy to take any question you may have.
Thank you very much, Jim. Sorry. I think we'll have now opportunity also in the panel to discuss on the main advantages and drawbacks and what is the potential of the biocatalytic technologies. But of course, we can just now take the moment for any questions that the audience may have. Does anybody want to ask anything before we go to the panel? Nothing? Okay. No, also the online participants don't have any questions. So maybe, Jim, you can stay now with us, and we may start the panel. I think we can just take over from what you have just presented. So may I ask that the panelists may come forward? Daniele, Koen, and also Ghent. Thank you. Step forward and separate a little bit. Okay. So this panel will be kind of an open discussion with us. We'll just prepare some general questions, but not that they have the straightforward answer from your side, but also to open a discussion with us, also with our panel. So also our audience. So feel free also to raise your hand and bring forth any comment or anything that you may find useful for our discussion. And so, well, I think that the only one that needs to be introduced is Ghent.
Yes, that's me.
It's our expert also in animal nutrition and functional ingredients, and he's working in nutrition science and also been with us in BIOCON-CO2 since the very beginning and participating mainly in the downstream work packages and tasks. And sorry, I will just turn the speakers to you.
But
do you have all?
I think
then let's choose in the public, and I'll just ask to be a little bit louder in case you want to ask any questions. So first topic we have here, as I said, it will just be general questions, so feel free to interact whenever you would like. Maybe this question we can start with you, Daniele, and then if we can also provide the discussion with the rest of them. First thing we have here just to discuss how BioCCU technologies can compete with other electrochemical and catalytic processes to convert CO2 into valuable products. So it's also very interesting to take over from Jim's presentation. I don't know if you can just provide any insight from your side, and then maybe Jim, you can be also rebutting whatever is here. So.
Okay, thank you, Xavi. And well, I don't know if everybody know me.
Yes, Daniel, sorry, I didn't introduce you. So
no problem. I can introduce myself.
Just like that. No, of course. Sorry. What's that? Yeah.
Nice to know you, all of you. I'm Daniele Molognoni. I work together with Xavi Monce at Leitat. I'm in the Department of Energy Engineering, and I'm mainly working with bioelectrochemical systems. In this project, I was focused on tasks related with electrofermentation in work package 3. So my background is more about the energy sector, but it is very coherent with all the topic here and all the talks of this morning. And regarding this question about the differences and the competition between biological CCU and the other technologies of electrochemical catalytic processes, both Koen and Jim talked about these differences in their talks. Of course, electrochemical and catalytical processes are more at a higher TRL. They are more near to, or they are industrially, they are already used. But they have some constraints, mainly due to the catalysts that can be poisoned, the use of raw materials, and the biological conversion of CO2 may help in these aspects. They can work at mild, at more near to environmental conditions, and they may be resilient to impurities. And this I saw it myself in my research related with biomethane production. And I think these are the advantages of biological processes versus the chemical ones. I don't know if.
Thank you, Daniela. Rest of the panel, no Jim or anyone in the panel, just to comment on the advantages also, apart from the drawbacks that we've seen from Jim's presentation.
Yes, maybe from my side, we are in a completely other business. We are in the feed business, so it means the low-end business. And to be honest, today it's mainly the cost that drives, because indeed we are responsible for food production, so the basis of everything for us. So when we have to choose between cost at one side and sustainability at the other side, that's a very difficult exercise. So the ecological and the economic balance is a very difficult one, especially now, especially in crisis situations like the Ukraine situation today, where the raw material prices are skyrocketing. We have to make choices, and in this case, it's cost, because we need all food. Yeah. To give you an idea, when we have the conventional processes, in this case we talk for the conventional feed additives, like for instance we have lactic acid, formic acid, even the fatty acids that are available now, that are all produced by or conventional extraction technologies from plants, or biological, and means microbial, like lactic acid. These technologies are still today the most viable ones, because at the end it can only cost 1 to 5 euros per kilogram. Yeah. So when we have today the technologies available from the CCU, they are not yet mature enough. Yeah. When we transform it towards protein at the other side, then soy, yes, soy is still the reference. So there indeed we are continuously in a fight against the ecological dimension as well as the economic dimension. Yeah. So if the answer is, if the question is, do you believe in bio-CCU? Yes. Has it a chance to be viable today? No. For our business.
Yeah, mainly for, it's in the vision of how potential it is in comparison from the existing ones. Yep. Jim has made quite a speech for that. They have these are potential technologies which are very, very much mature, but we need still to be working on this. I know also Jim or any other ones that what you think after what we have obtained in the project, what is the space beyond, what are the potential in the following years to continue with this technology and with different applications, more than what we have studied in the project. I don't know if anybody from the panel has any other insight before going to the next topic, and also we can open the space for any question or any comment that you may have in the audience.
Maybe to add from my side, if the question is, can bio-CCU compete with chemical CCU? I don't think it's about competing with each other. As you've seen also from the talk of Jim, the products that are made from bio-CCU and chemical CCU are very different. And indeed, it really depends on which products you want to target. Some products are not able to be made by chemical CCU. single-cell protein, PHB, these kind of molecules. So BioCCU can really leverage on that, I think. If with BioCCU we target these, let's say, energy kind of molecules like fuels, then it's difficult to compete with chemical CCU, that's for sure. But depending on the product that you target, BioCCU can really have an edge. And then I also think that these kind of processes can go hand in hand. With chemical CCU, that's all, Jim also said it, the potential of converting a lot of CO2 is way higher. You need less capex, less big, smaller reactors and so on. You can convert a lot of CO2. If that's your target, very good, go for chemical. But then you can, if you then make methanol from it, methanol can be a source for biological processes. It's not it's not gas fermentation, it's aerobic processes. But then you can leverage both technologies. You convert a lot of CO2 chemically to methanol, and then the methanol is transformed via aerobic fermentation into a range. Yeah, the sky is the limit. You can do whatever you want with biotech. So I think it's not about competing. It's about putting the correct solution in the correct place, depending on a lot of factors. And these technologies can also go hand in hand.
Thank you very much, Juan. Very interesting. I don't know if, Jim, I think you had some comments to add here.
Yes, in fact, I think that the point of view is very valid to say that we are not obliged to see them competing, but maybe to see them focusing on different markets for molecules and maybe going even hand in hand. As we mentioned, we can have this kind of thermochemical processes to produce lots of precursor that then can be used for the energy or as a precursor for another production using bio-CCU. And thereby you avoid the limitations which are linked to the mass transfer and so on. Also, I think that thermocatalytic technologies, they rely on concepts and on things, catalysts, processes that have been, for which we have a global knowledge that dates back a century. And so we know that space as chemical engineers very well, and so we know how to push it to the efficiency limits and so on. On the other hand, I think, and that's my feeling, that bio-CCU and biology is more a nascent topic where we still have a lot to research, still a lot to understand. It's much more complicated, but it also holds a large potential. So I think that we have a maturity difference also between the two different technologies, which link to the fact that we have less experience, globally speaking, with biological systems. And I would like also to rebound a bit on the point of Ghent on the crisis which is affecting material. On the energy basics, we also have a crisis for energy, but this in fact goes in favor of CCU because CCU is produced using renewable energy, and the cost of producing renewable energy has changed a bit with the commodity prices of material, of steel and so on, but not so much. And what changed a lot is the counterparts, the fossil counterparts. Back then, we were doing techno-economic assessments, we were doing business cases with a natural gas price of 20 euro per megawatt hour, and nothing beats that. But when it goes to 100, then we are talking about something that is beatable, and there we can find some nice opportunities. It also sparked the willing to change and to stop having this kind of dependencies from industries, from all kind of stakeholders.
Thanks, Jim. It's very interesting insights. I got another question for you, if you don't mind. So, in the vision of a company, such a company like yours, what is the resistance that you find, like in the more maybe in the top management, to invest in these kind of technologies? You know, so it's, as you said, the vision of the expertise you have, the readiness, but you're here also, you know, and you're part of this consortium. So what is, in general terms, the resistance that you have found in your own company, maybe in the top management, on the overall strategy to maybe think of in some years to invest in this such a technology that it's not very much ready yet? And what is your...
Maybe to start this answer, I'm just a humble project engineer, so I don't want to have I'm not representing NG and the global reflection of the group. But indeed, what we have faced is, well, these emerging technologies, they always take a lot of convincing to middle managers, and top managers, it takes even longer because you need to build your case enough in order to reach them, and when you reach them, they have so little time that it's often hard to have an edge on making the case for new kind of working, and especially when you're talking about biological aspects. Well, they don't know anything. They are into electricity generation, into gas transmission, so it's often very not easy to get this understanding. So first, the first battle is to try to make the battle for the usefulness of developing these projects, and this takes months, this takes years. I think we have been working on e-fuels for already 3 to 5 years, and we are only trying to develop these projects now. We are reaching a common understanding that this is a nice opportunity for NG to look into. So it takes long. Now, when it comes to BIOCCU more precisely, so we have the chance of developing these large-scale industrial projects. We have already tackled feasibility studies. Now we are moving on to more basic engineering studies. And so there you look into technology providers which need to produce a technology which must be strong enough to justify an investment decision. These projects are multi-100 million euro project, CapEx. And CapEx is not the big part of the cost in the end. It's electricity that is the big cost. So these involve a very high financial risk. So I do not have a crystal ball. I don't know if we will go through them because they are highly risky. But we need to have some gut feeling that the partners we're developing this kind of project with, and indeed the most risky part is the conversion of the CO2 and the hydrogen to the added value molecule. Mm-hmm. We need to make sure that these stakeholders are strong enough. And so again, coming to some things I have already said, when we look at the thermocatalytic space of technology developers, these guys, well, you have some big names in there. You have MAN, you have Haldo Topso. These guys, they know how to do industrial projects. They can manage the risks. They can give warranties and so on. When you look at BIOCCU, we have been in extensive discussion with Electro-Kia, for example, when we look at e-methane production. Mm-hmm. Well, it's a bit harder, and you cannot compare them to other stakeholders, and so this is something we have faced. And in fact, Columbus was considering biomethanation, but it was decided by project managers to quit that because of the risk that was embedded in working in this nascent field.
Very nice, James. Thank you. I don't know if any of the panel has any insights of this also. Maybe
maybe
go ahead.
From our side, indeed, when we talk about the potential resistance in companies, indeed the capex, so the investment cost. I think that's a huge one. Also, it's out of a comfort zone of our industry because we are used to pelletize, to mix all these things. So it's complete other technology. So it's also a little bit the fear about the technology, and our investors are not used to that. But also two other important parameters are, for instance, the safety of the compounds, because at the end they end up in the food chain. And as we have seen, several of these gases still contain sulfates, all kinds of potential toxic substances, and to see how we deal with that. So it's not an easy way towards going to a GMP plus environment. So that's also a potential concern. At the other hand, like we have also seen in the presentation of Jean-Luc van der Arkema, besides the capex, it's also the end price of the product. Today, in the volatile markets, we cannot predict what can be the price within a few years of these types of products. That's also another concern from our side.
Very nice. Also, again,
Yeah, we just add also, because again, I'm rebounding what Ghent mentioned, the legislation is very important, very key. I don't know too much about the feed legislation, but when we talk about this kind of CCU project, indeed, how do they interface with an ETS? How will this be framed as a renewable fuel in the future? And this kind of things is indeed very important. And currently we are in a bit of gray zone where we don't know exactly how these legislation and regulation efforts will frame this kind of molecules. And this other uncertainty, which is always bad when we talk about investment decisions.
Yeah, thank you, Jim, because this goes directly to one of the questions we had in mind. I think we've mentioned in several of our presentations before, but just to, again, place it here on the table, which are the critical risks for companies to invest in BioCCU? I don't know who would start. Just one of these, of course, is legislation. Maybe Kun, if you...
Yeah, I think already many risks have been mentioned, legislative, also technological risks, also policy. Tomorrow we will have a session on policy. Also there are risks. The policy changes from time to time as well. And if you build your business case based on the fact that you will get a premium or something on a green product, and suddenly it's not a green product anymore, then your business case is gone. So kind of stability of the policy would help. Good policies and then stability of the policy would be very good. And then, if we talk about technological risks, let's say low TRLs, there are a lot of technological risks in the lab. They can be managed. They can be managed with not a lot of money to invest. So that's good. But then if you want to go to a commercial scale, you have to bridge from low TRL to high TRL, and how are we going to do that? Because in the middle, there is this phase where the technological risks are still pretty high, and the money that you need to deburden the technology is also very high, and investors don't like this. I think that's a bit where we come in then with BIOCON-CO2 and with the pilot, and with Biobase in general, to try to bridge this gap. I think this is one of the main steps, like these open access pilot facilities. These can really bring a disruptive, step in commercializing these kind of technologies.
And now that you mentioned the technological risk, it's something that was pending from your presentation. You just talk about the value of that. You've talked about very much what the achievement of our pilot, which is, I think, it's one of the main outcomes of the project. I don't know if you would a little bit brief, very generally to the audience, which was the main bottlenecks, because we all know in biological processes and bioreactors how hard it is to scale it up. Maybe just comment the main bottlenecks that you found on this process.
On the process of designing and constructing the pilot?
And also for bringing the process in a higher scale. Which is always
on the I can go very broad in this. We know we are very used to doing gas fermentation on a lab scale, but if you scale it up, you have to pump in a different way. You have to aerate your fermenters in a different way. They suddenly have to be pressurizable up to high pressures, and your valves, your typical valves, cannot handle that. And there is a whole lot of things that you need to take into account when you go to bigger scales. And then, of course, costs and safety, especially safety as well, is a very big very big burden, and the more safety. Yeah, safety is the most important thing. It's always a balance. We want flexibility, we want safety, and we want low costs. But these things don't really go together. It's a difficult triangle to manage. So yeah, also with safety, we've seen a lot of additional precautions that we needed to take. Also, working at the site of ArcelorMittal then requires us to take even more measures than we are used to. Soon, in half a year, we will move the plant to Finland, to a gasification plant. The safety and technological burdens will start over again, and we will have to find engineering possibilities to cope with this. So yeah, there's a lot to think about, but it's very interesting.
Thank you, Gwen. I don't know if you... Yes, Andreas, you can speak a little bit loud, and that's for the online.
Yeah, thank you very much so far. I just thought, okay, now we've been through a project, and I think it was also a kind of experiment where you had many external factors changing so much, like we've been through the pandemic crisis, we now having this war. Does these external factors in the industry change the view on high risk developments, like more risky developments like BIOCON-CO2? Is the discussion or another awareness of this due to these external factors, and maybe you could observe this during the project?
I can get lost in that. Indeed, a view of a company changed in that instead of being resilient, we want to become anti-fragile. We thought we were anti-fragile. This was identified by resilient, but we see that resilience is not sufficient anymore. Yeah? We want to de-risk and decarbonize, and also de-risk for the company. So that's indeed an important move that COVID, as well as Ukraine wars, Ukraine war, not multiple Ukraine war, has created. Yeah, that's true. Yeah. So changing, in fact, the mindset from resilience towards anti-fragility. Yeah. And for instance, the container and Suez channels that blocked the ship in the Suez channel 2 years ago, realized that we thought in the globalization world that we were quite resilient, but it's not sufficient. Yeah. So moving more and more to regional as well is also a trend to cope with logistic problems. Yeah.
Yes, Anna, go ahead.
My question is very similar. I am curious about the position of ENGIE also after this crisis that we are having, this energy crisis, and will that have an impact? Do you expect an impact on the strategy of ENGIE?
Yes, indeed. So again, I'm not project engineer, so I don't want to be the herald of the strategy of ENGIE, because I would say some things that are not correct. But yes, indeed, it does change the picture. Again, as I mentioned, we had business models which were to be compared to a gas price at 20 euro per megawatt hour. Now we are much higher, so this reshuffles the cards, and this makes alternatives much more interesting than what we had before. So that means that we are accelerating the development of different ways of managing energy. So that means that, for example, at ENGIE, we are increasing LNG shipments from different sources, which we were not doing before. We are also developing quite aggressively biomethane production, for example, and this kind of things, and hydrogen, indeed. Again, we have the competition is not there. Well, it's easier than before, and so this is how strategically it changes. Basically, the energy crisis, and again, it's a bit like Geert mentioned. We were fragile because we were exposed to these shipments from Russia. Well, now we need to find ways to avoid this kind of fragility, though still by by ensuring energy access to our clients and to keep the business going. But now we need to find other ways to do it, and we need to, and for example, also renewable energy is a good way to harbor our energy production back home, and to try to having this decentralization is a nice way to also avoid having just one pipeline being between Russia and Western Europe. So yeah, this is a bit how it impacted us.
Thank you. Do you have any also insights on this before, or maybe we can just move to another question? There was another, maybe a short debate we can open also on the way when we think of CO2 as the raw material of this kind of processes. So how do we link the needs of CO2 with for the bioprocess with the availability of CO2 also? And here we can think about two models, maybe decentralized bioconversion or building hubs of CO2 producers. What insights maybe you would have? Maybe we can start, Daniela, with this.
Well, from my knowledge, the CO2 capture is more economically convenient in concentrated sources. So I would say that hubs of CO2 producers would be a better scenario from my knowledge. On the other hand, having a distributed capture would require the development of systems of CO2 capture that can work well with a diluted source, with a low CO2 concentration. That's my point of view.
Anybody against, in favor of this?
I don't have any preference in terms of,
because potential.
Decentralized.
Potential.
I think it depends on different factors. It depends on the country structure. I can imagine when you have a really industrialized country, then it's better to do it indeed in that country instead of suburban areas where you have only agriculture. At the other hand, you have also to see it in policy systems, like combined with carbon credits, and see where you can also develop trading systems. And this can be also next business model behind that. So there are different possibilities, I should say, to the business developers in the room. Start to be creative and try to create some business models behind it. And then we can work together. Because it's not a standalone problem. It's a multi-actor approach. And we have to think outside the box, not in terms of conventional processes or products, but also in terms of novel trading systems, like for instance carbon credits. Yeah.
Quite nice sense. Any insight on this that you would like to? Yes, Jim. Sorry.
Yes, no problem. Yes, I agree with what has been said. So indeed, carbon capture is the cost of carbon capture is it is lower for higher concentrated CO2 sources, and so you have a driver for CO2 capture cost to go to concentrated sources, and it also leverages interesting effects of scale. So you want to go bigger than smaller. And this also motivates what we have seen currently emerging, this kind of hubs being developed in heavy industrialized areas such as harbors in the North Sea port, in Rotterdam, also in England. And so this will be a source of CO2, though that CO2 will mainly go to storage because we have these huge amounts. We are talking megatons. And we are seeing this emergence of the storage business model. So actors developing the storage part and not the upstream part. So saying people like Northern Lights saying, okay, give us your CO2, we'll manage it, we'll store it, and you just have to pay a fee for that. And so this kind of business models, because they also leverage huge infrastructures, you need huge pipelines, you need the offshore platforms to inject it into the storage. This will probably emerge as a centralized infrastructure, though it can also interface with CCU and thus with BIOCCU. And this is typically what we are saying in one of the 3 projects we are developing, the REUS project with ArcelorMittal in Dunkirk, where the main, there are 2 projects in parallel. There is a project to develop a CCS process chain with Northern Lights, in fact, to capture the CO2 and export it for storage. And in fact, REUS, the second project for CCU, will plug in that process chain to divert part of this CO2 for the CCU. I think it will also depend, for when we are talking about CCU, it will depend on the policy aspect, as we are seeing a movement from the regulatory bodies to try to incentivize, and this is maybe a euphemism, maybe it will be to oblige CCU to use sustainable CO2. So that means CO2 that is not fossil-based, so CO2 captured from the atmosphere, from biogenic sources, or from mineral process sources. And so that means that when we are thinking about the 2 first, these will mostly be decentralized and not on these kinds of hubs. DAC can be decentralized anywhere where you have atmosphere, this means basically anywhere, and where you have low carbon renewable energy sources. Biogenic CO2, except big fermentation processes, you also have lots of different infrastructures that could be interesting. And in that aspect, I think that biomethane infrastructure are very interesting, because you have the bio-CO2, which is a waste of the process. It is already pure, you can use it, but then it's decentralized, it's small scale. And so maybe BioCCU will emerge more in this kind of aspects where we have this decentralization of the assets.
Thank you, Jim, for these nice insights. I don't know where you have any. I think it was very complete and a very nice vision for the future. Also to think about the new business models. It's very interesting. We haven't really been talking much in BIOCON-CO2. It's still a bit far from that, but of course it's something to be considered. Any questions, insights? No. There was still a question, but I think mostly we have covered everything that we were thinking about. Of course, this is open to open it for new debates or anything that needs to be done. Also, we hope that Jean-Luc could be here, because he would have brought so many nice insights. We were talking about also, this is from the point of view of the raw material, but also with the point of view of the products. There was also some other other discussions that may arise. But we've covered mostly everything, because also in the presentations we've been talking about the biofuels, which are also it's a more mature process. But we are talking about also bioplastics, and also how is the potential for the processes that we've been developing, or we've been trying to develop in BIOCON-CO2 and BioCCU for bioplastics, feed, food products. Do we have any additional insights to bring here to the audience in what is the potential for, and in the point of view for the products, basically? I think you've mentioned it before, but
and I think the BIOCON-CO2 project was some kind of nice pilot to see where we can head for, and we see it rather as some kind of feasibility study to see what can we do, what are the risks, what are the dangers, what are the potentials as well. And now at European level there are a lot of new projects granted, like for instance Vivaldi as an example, but also many others. Let's make the pitfalls that we had here as opportunities for these projects, so that we don't make the same pitfalls, but also the success stories that we had in this project, because there were also successes created in this project, although maybe only at lab scale or demo scale, like for instance what you said at ArcelorMittal. Let's use also these positive learnings for these projects, and let's build this world together at the end.
Completely agree. I don't know. You want to complete a little bit on this? Yes. Anything to be brought on this? Maybe we have to develop on these success stories, of course. Yes, Aline?
Yes, I would have a question. So we talked a lot about the interests of the industry and the effects by the crisis and the COVID, but we also have two partners from later there, which is on the scientific part of you, and BBPP, which is like in the combination. Do you see an effect currently out of the crisis, or do you see an increasing interest in BIOCCU projects, or do you see already a decrease of interest in these areas?
From my point of view, for the time that I have been working in BIOCCU, I think it has only gone up, the interest. I think this is I don't have the numbers to state or to prove this, but from experience, I really have the feeling that a lot is going on in this kind of technologies, and yeah, probably it has to do with reducing our dependence on fossil fuels. Yeah, and maybe not BIOCCU then, but then our business at Bio-based Europe Pilot Plant has only benefited from the last years. I don't know if that is. Even during COVID, we thought, okay, the companies will have a hard time. They might divest in R&D. Not the case. It only went up. The amount of projects that we're getting in, maybe the biotech industry is just getting bigger, independent of crises, but we don't see any negative effects from the crises in terms of amount of R&D projects that are coming to our plant. That's good to see, I think.
Also, completing on this, the interests has been driven mostly from the available calls or topics that came out the recent years, or you have also detected this in maybe private projects that you may have with companies directly developing a project for BIOCCU on the carbonizing.
In terms of BIOCCU, yeah, there is also more and more interest from private companies, and mainly from technology developers, because they really have an interest to scale up and don't have the equipment for it. The interest for BIOCCU doesn't, for private collaboration, doesn't come from the big industries, because there's too much risk in that for them. But from the technology developers, yes, there is an increased request for projects as well there. Yeah.
No, Daniel, in a late touch point. We saw the same with the last years at both levels of public funding or private interest of companies related with energy. And well, in my personal case with biogas, biomethane, improvement of anaerobic digesters for producing biomethane, for collecting this CO2 instead of just eliminating from the product and valorizing it. A huge increase of interest and of investment in this topic.
Okay. Yes, Montse.
Also, we have been seeing during several presentations that CO2 or research on CO2 and bioconversion techniques cannot be alone, because it highly depends on other technologies, low carbon energy technologies, and also green hydrogen production. So I think that it's something that has to change, and a lot of investment and a lot of research are being made during these last years, and will be more in the future. So we need to link both kinds of research in order to be able to exploit the potential of this BIOCCU, because as we have seen, hydrogen is one of the most costly effect or issues to take into account also for the productive industry and so on. I think that it's something that is interesting to try to link and combine, and also Jean mentioned during his presentation, this link between hydrogen and CO2. So it's something that we need to think of that.
Any more insight? I think yes, we have. I think I'll just make you approach in order to be heard.
I hope I'm being heard now.
I think so. Maybe Jim.
So,
Yes, great.
Thank you. So thank you for this input on your focusing on the private sector drivers for the growth of BIOCCU. I'd like to invite you to chime into tomorrow's panel discussion as well, where we will talk a bit more about financial instruments and incentives to further assist the development of these technologies. And I think another driver behind the BIOCCU technology development is not just the mitigation of fossil fuels dependency, but also the critical raw materials. I mean, we also have we have CO2 emissions everywhere in human societies, but we can also grow microbes almost everywhere where humans live. So not just CO2 is abundant, but microbes are also abundant, and I think that's a key combination behind these two. We're not too dependent on scarce chemicals, on rare earth metals and such. So that's a technology that combines two widely abundant resources. I think that's a key feature.
Thanks so much, Espina. I don't know if you from the panel have any insights on this. Or Marcel?
I think yes, maybe I can
sorry.
say a word on that. I agree, and at the same time, can you hear me?
Yes, perfectly.
Okay, because the image is frozen. Okay, I agree, and at the same time, the analysis that we had is that basically the main difference is on the core, the catalyst. So indeed, with the biocatalysts, you are talking about carbon, hydrogen, oxygen, nitrogen, a bit of sulfur maybe. But for thermocatalytic, you're talking about metals. Though when you look at the metals that you use, these are not, well, there is always a trade-off to find, and most of the time between cost and productivity, efficiency, and so on, and performances. And most of the time, this leans towards the cost. And so we are talking about using nickel, we are talking about using cobalt, a bit of cobalt. But you're not supposed to use your catalyst. You will degrade it a bit in time, but you're not supposed to use it. And you need very little amounts when taken into perspective. This, for example, if Fischer-Tropsch were to be developed on a large scale, this will not drive significantly cobalt as would EVs, for example, do. And when you're doing the comparison with bioconversion, also, you need to factor in the fact that you need larger infrastructures for the same amount of CO2 that is converted. So that means also an increased amount of steel, needs to be stainless, needs to involve nickel in the alloy, and so on. So I think it's not so straightforward, and this was a positive point we had seen to begin with. But after reflection, I think it's more debatable. I don't think there is a clear winner on that aspect.
Thank you, Tim. I think Marcel also had a comment.
Yeah, what I think needs to be considered, carbon dioxide is a resource you need, biology is a resource you need, but water. So for electrolysis, we need a lot of water. Yes, there is carbon dioxide emission at different sites. There's biology available at a lot of sites, but there's no water available. And what we also have to consider, BIOCCU needs, in most aspects, hydrogen to convert carbon dioxide, a lot of hydrogen, and we are not the only users of hydrogen. So supplying sufficient water and sufficient electricity to meet the demands of hydrogen is basically, is a big challenge. So, yeah.
Yeah, completely true. This was something we have not seen emerging, but developing the 3 projects I have mentioned, talking with the public bodies that are involved in the regional aspects, this was something that was very strong from them. Can you decrease the demand in water? And this is indeed something you can do to some extent, because all these hydrogenation reaction co-produces water. So you can, this is also maybe a point in favor of CCU versus hydrogen, because at the production, you recover part of the water. And it's not, when we're talking about energy application, hydrogen is oxidized into water back and just emitted to the atmosphere. So it's kind of an open cycle. While with CCU, you recycle part of the water. But it's true that it's a very important point. And we're especially surprised in Dunkirk, where, well, you can think about Dunkirk being rain heavy, but nonetheless, the public bodies were very stringent on the amount of water that we can use. And it's too much is a no-go for the project.
Thank you, Jim. I think that for now, I think we'll kind of close the session. We are now, it's 12:30, so I think it's time now to close it. Just to conclude with the insights that you've been given, just as a whole summary, and then I think tomorrow the conclusions will be also in that sense. From the presentations we had and from the interesting comments from our panelists, we've seen that BioCCU now it's placed like in the center for opportunities, but also threats and risks. So right now, of course, the main point that we've been mentioning all the time is the technology readiness. So it's still, there's a lot of work to do in terms of taking over some bottlenecks, also designing the proper business model to be competitive. You mentioned the price. I think it's right now with the turbulent situation and the supply crisis, also the product crisis and the raw materials crisis it's something that needs to be considered right now for the next years. And also, if more or less, these are the comments I wanted to mention. I don't know if I'm just missing something very, very key to mention. I think everything was covered so far.
Right business model.
Of course. But this is or the different business models as Jim mentioned, and also depending on the geographical situation and the needs of all the particular places and points and industries. So thanks so much for your attention, and we will resume the session later on. I think it's at 2 exactly. So thanks so much. And okay. Well, welcome back, everybody, from the audience here, also the online audience. Right now, we're going to start with the science session that will last all the afternoon until the end of the first day. Sorry. So, right now, Ana Lopez from Wageningen University is going to take over and will host the session and present all the speakers and the last panel that we'll have today. So Ana, whenever you want, the floor is yours. Thank you.
Thank you. Welcome everyone to the second session of today. It will be the science session, so we will present some of the results of the project. There will be 4 presentations in total in this session, the first 3 ones before the coffee break. And the first presentation will be given by Dr. Gabriele Phillips, who is a scientist at the Department of Industrial Biotechnology at the Fraunhofer Institute for Molecular Biology and Applied Ecology in Aachen. They are a partner of the project. Gabriele obtained her PhD in 2011 on a study on green hydrogen production using microalgae, and she's working now on white biotechnology and especially in biological production of fuels and chemicals from syngas using Clostridium. She has a lot of experience on cultivation, metabolic engineering, and syngas fermentation using these organisms. And she will present the results that we obtained with the microbial cell factories in the process. So in this project. So yeah, please go ahead, Gabriele.
Thanks for the nice introduction. So dear project partners and dear guests, I will now present some of the results obtained during the course of the BIOCON-CO2 project using microbial cell factories for the production of our targeted products with CO2 as carbon source. The aim of the project is the valorization of mainly carbon dioxide derived from industrial process gases, for example, from the steel industry, to produce different biochemicals. And this can be done via different technologies. And among these would be the fermentation of microbes that have been engineered for an increased production of the desired products. Alternatively, another specific type of fermentation can be used, which would be the electrofermentation process. And last but not least, not only entire microbial cell factories can be used, but also isolated enzymes, which are combined for a specific reaction towards the desired products. And in the BIOCON-CO2 project, we have targeted several of these molecules. Among these are C3 to C6 alcohols, like the isopropanol, butanol, and hexanol. But also acids were targeted, like 3-hydroxypropionic acid, formic acid, and lactic acid. And all these chemicals are molecules that are interesting for the chemical industry, and they can be used in different industry sectors. For example, as chemical building block for the chemical industry, or in the food and feed sector, or in the transportation sector. I will now focus on one of the different technologies, which would be the metabolic engineering of Clostridium lungdalii for the production of butanol and hexanol from carbon dioxide as a carbon source and hydrogen as energy source. Later on, I will give an overview on further technologies and give some examples of the results of the project partners. In our case, the main aim was the utilization of carbon dioxide as carbon source for the microbial production of butanol and hexanol with high titers. And therefore, we focused on the utilization of Clostridium lungdalii, which is an acetogenic bacterium which can use syngas and carbon dioxide as carbon source. And this can be done via the Wood-Lungdal pathway. And the advantage of this organism is that it can be metabolically engineered. And further on, we aimed at a stable expression strain, as this would be necessary for continuous fermentation. Our strategy was using a synthetic biology approach for the production of the different biochemicals. And therefore, it is necessary to select different genes which are useful for the pathway of interest. And the genes have to be amplified and have to be cloned into shuttle plasmid. And this allows then to introduce the very large plasmids via conjugation from our cloning strain E. coli to the recipient strain, which is Clostridium lungdalii. And to allow then a stable expression for continuous fermentation, it is necessary to introduce the genes into the genome of the host organism. This allows also a stable fermentation without the addition of antibiotics, which is quite an immense cost factor. And then several rounds of strain development can be followed. These can be done either, for example, by adding several additional genes, or by replacing promoter sequences, or even knocking out of genes of competing pathways. And once an optimized strain is obtained, then the fermentation in bigger scale can be done in the fermenter with syngas as substrate. And later on, it needs to be upscaled to obtain a sufficient amount for downstream processing and to purify later on the desired products. So, as mentioned, we aimed at the production of butanol and hexanol, and therefore we were searching for suitable genes. And we knew from literature that Clostridium cloyveri produces quite high amounts of butyrate and caproate. And in this biosynthesis pathway, butyryl-CoA and hexanoyl-CoA are important intermediates, which are the same intermediates like for the production of butanol and hexanol when you add a reduction step. So to get a deeper insight whether this could be a good strategy, we cultivated Clostridium cloyveri and analyzed the intermediates of the strain. And indeed, we could find reasonable amounts of butyryl-CoA and hexanol-CoA in the strain. Hence, we considered the cloyveri genes as a promising basis for butanol and hexanol biosynthesis. Hence, we cloned the genes for butyryl-CoA and hexanol-CoA biosynthesis from Clostridium cloyveri. And we also added a gene, an alcohol dehydrogenase from Clostridium acidobotulicum. And this enzyme was known to be able to convert butyryl-CoA to butanol and hexanoyl-CoA to hexanol. So all these genes were placed and cloned in our in-house shuttle plasmid together with one resistance marker, the ARM-C gene. And we also used transposase, the HEMA transposase, which allows the random integration of all the genes which are placed between two specific recognition sites into the host genome. Yeah, we transformed our Clostridium lungdalii with PIM-hex15 plasmid via conjugation, and this strain was already at hand at the start of the project, and so we continued with the genomic integration of the strain, and and then we cultivated and compared both strains, the plasmid-based strain and the genomic integration strain in small scale by cultivating them in serum bottles. And we analyzed the fermentation products. And indeed, we could see that in comparison to the plasmid-based strain, the genomic integration strain showed an increase in butanol and hexanol production. And we further continued with cultivation in a larger scale in a 2-liter fermenter. And we could verify and the increase in product titer of butanol and hexanol of the genomic integration strain. And additionally, we saw that in a larger scale, we even obtained higher titers for both products. Yeah, to get a deeper insight into the black box bacterium, we performed targeted proteomics analysis, and these were conducted in a 2-liter fermentation scale, and we took samples at different time points of the fermentation, and took a closer look on, we quantified the amount specifically of the enzymes which are encoded on our plasmid, either on the plasmid-based strain or integrated into the genome in the genomic integration strain. And we could see, although both strains in the early phase had a similar amount of proteins, the protein level decreased in the plasmid-based strain, but it increased in the genomic integration strain. Furthermore, we could recognize that those proteins which are more or less controlled by the PTB promoter showed a lower amount of expression than those proteins which are under control of the PTA-ACK and the PCODH promoter. So we concluded that the lower enzyme expression of the cluster, specifically under the PTB promoter, could be one bottleneck for the production in for the product titer. So we decided to integrate a second cluster. And just to give a short overview, the before mentioned genomic integration strain had the complete butanohexanol biosynthesis cluster comprising about 18 kilo base pairs were integrated into the genome of Clostridium mondalii. And during this integration, we could select for the strain using the ARMC gene, but this had to be removed for further strain development. And therefore, we used a CRISPR-Cas9 system, which was developed in our group, specifically for Clostridium mondalii. And we could then continue with further metabolic engineering by introducing a second biosynthesis cluster, which was derived from Clostridium carboxylivorans, as it was known from literature that this cluster allows butanol biosynthesis. To evaluate the effect of the second biosynthesis cluster, we compared the two strains, the single genomic integration strain with a double integration strain. And this was done in a small-scale cultivation in serum bottles. And indeed, we could see that the amount of hexanol increased in the double genomic integration strain, but at the expense of butanol production. Furthermore, we knew from other experiments that a lower cultivation temperature at about 30 degrees could be beneficial for hexanol production. And so we compared the strains in both conditions, and we could see that at lower cultivation temperatures, an increase in hexanol production. And we could obtain, in this case, 251 milligram per liter. We then scaled up this process in a 2-liter scale in the fermenter. And the genomic integration strain was grown at 30 degrees with different pH profiles. In one fermenter, we kept the pH regulated at pH 6 constant, and we could not see in the first time butanol hexanol. But as soon as we stopped the pH regulation and allowed the acidification of the medium, we could see the emergence of butanol and hexanol. So we also did another fermentation where we allowed the natural acidification during the fermentation up to a pH of 4.75. And here we could see a clear increase in product titer. And we could also see that the natural acidification triggers alcohol production in the double genomic integration strain. So to sum up, we could show that we can engineer Clostridium lungdali Y type, which does not produce butanol or hexanol. For the heterologous hexanol and butanol production, obtaining 109 milligram per liter of butanol and 393 milligram of hexanol, and this was all on 20% of carbon dioxide and 80% of hydrogen as substrate and energy source. This was done using various steps of metabolic engineering and process development. And we are quite happy that we could publish this just recently in the journal Microbial Cell Factories. To conclude, we show the proof of concept for the valorization of carbon dioxide for the production of C4 and C6 alcohols. And we could see that a stable expression was possible without the addition of antibiotics, thanks to the use of genomic integration. And we also saw that different product ratios can be obtained depending on which strain is used or which process parameters were used. So further optimization steps can be undertaken. Among these would be, for example, the change of the promoter or RBS regions, or several new genes could be added or deleted to force the flux into the pathway and reduce competing pathways. And further optimization steps could be the process, to optimize the process parameters and the medium composition, and an increase in biomass would be favorable probably for an increased product titer. In the next section I will show the strategy that has been followed by Ana Lopez Contreras from Wageningen. And her strategy is to develop and metabolic engineer solventogenic strains for the use of carbon dioxide containing gases. Clostridium beijerinckii was used as the solventogenic strain, and it produces a mixture of acetone, butanol and ethanol, and during the process called ABE fermentation. And the strain uses glucose as the carbon source. And in order to engineer this solventogenic bacterium for the use of carbon dioxide, the missing genes in the Wood-Lungdal pathway, so the carbon dioxide fixation pathway, need to be identified. And so the genes for the acetyl-CoA synthase and the CO dehydrogenase and the methyltransferase are missing. And the ACSA gene was cloned into a vector under the control of the strong TA promoter and was transformed into Clostridium beijerinckii. And furthermore, the first step of carbon dioxide fixation was the gene for the formate dehydrogenase from Thiobacillus was used, which has a high carbon dioxide conversion efficiency. And this gene was codon optimized and also cloned into the vector and transformed into Clostridium beijerinckii. And the characterization of the mutants is now ongoing. Another strategy for the indirect utilization of carbon dioxide is by using co-cultures and the common product and substrate acetate. And in this approach, the fermentation occurs in two phases. In the first phase, acetogenic bacteria like Clostridium autoethanogenum or Clostridium lungdalii are used with gas mixtures with 80% of hydrogen and 20% of carbon dioxide. And at the end of this first phase, the reactor is inoculated with Clostridium acidobutylicum, and furthermore glucose is added. And using the glucose and the acetate as substrate, then this Clostridium mix produces butanol and also isopropanol. Both are products which are targeted on our project. And so the proof of concept of production of butanol and isopropanol by these co-cultures could be shown. The main achievements of this project part are the identification of CO2 utilization genes which are needed for solventogenic bacteria, and the CODH gene and the formate dehydrogenase genes were cloned and transformed in Clostridium beijerinckii and are now under analysis. And furthermore, co-cultures with acetogenic and solventogenic bacteria were performed. And it could be shown that acetate from CO2 was produced and was utilized by solventogenic bacteria for the production of acetone, butanol, and ethanol. Furthermore, the tolerance of solventogens to impurities of raw gases were tested, and it could be shown that benzene, toluene, and xylene, which are present in real gases, did not show a toxic effect on the cultures even at higher concentrations. Beside the standard fermentation processes, there are also very specific fermentation setups, in this case the electrofermentation. And I will now show some results for the evaluation of the electrofermentation system for butanol production using Clostridium beijerinckii. And these results were obtained and gained by Leitert. And you can see here one example of this electrofermentation setup. Clostridium beijerinckii was used for the establishment of the cathodic electrofermentation system, and electrofermentation is an electrochemically influenced spontaneous fermentation, or in other words, an electrochemical process to control fermentation pathways using current. And these electrofermentation systems can be performed in single or double chamber bioelectrical systems, and depending on the mode of the electrode, you can differentiate between anodic and cathodic electrofermentation. And in the cathodic electrofermentation system, you have an additional electron supply which allows the raise of the NADH to NAD+ ratio. And this is considered to improve the butanol production and, for example, also the selectivity. And the advantage of the electrofermentation system would be that you can vary the redox potential of the fermentation broth, and you can, as already mentioned, manipulate the intracellular NADH to NAD+ ratio. And in the cathodic electrofermentation approach, in situ hydrogen production is possible, and this would provide an additional reducing power. Several approaches or experiments were conducted with different cathodic potentials applied with respect to a control where no cathode potential was applied. And the results show that at a cathode potential at minus 0.8 volt. The Clostridium strain had a higher growth rate, which was 56% higher than in the control. And also the butanol production was increased by 44%. This also led to an increase in fermentation time, and a decrease in fermentation time. Furthermore, experiments were conducted by the addition of redox mediators, as previous results showed that this could be beneficial for the transfer of, I can show it again, of the electrons between the bacteria and the cathode. So addition of the redox mediator neutral red also led to an increase in Clostridium growth rate and in the butanol production rate. Not only whole cells, as mentioned before, can be used for the biosynthesis of valuable chemicals. Another strategy involves the use of isolated enzymes, and in this case it was used for the formic acid production from CO2. And here I show some results from Tom Ewing, from Wageningen, and also from co-workers. Formic acid is an important C1 bulk chemical. It has applications in different sectors, like in the leather processing and animal feed, and it can be used as a chemical building block. And formic acid can be selectively produced by carbon dioxide using the formate dehydrogenase enzyme. And during this process, NADH is used as a cofactor, and as this cofactor is quite expensive, it needs to be regenerated to enable a cost-effective process. And this can be achieved by the conversion of glucose to gluconic acid via the glucose dehydrogenase. So an enzymatic system was developed for formate production using the formate dehydrogenase from Thiobacillus, which has an increased carbon dioxide reducing activity compared to other enzymes of this type. And when this formate dehydrogenase was combined with the glucose dehydrogenase, then it was possible to produce 0.8 gram per liter or 17 millimolar of formate within 46 hours from CO2. And it was also able to produce formate when mixtures of gas mimicking real steel mill of gases. But the titers were lower, they were around 4 millimolar. And this is assumed to be due to a lower carbon dioxide concentration, or it could be also due to the inhibition of the enzymes by carbon monoxide and or hydrogen. And in the future steps would be to increase the formate titers and the production rates by, for example, optimizing the enzymes. Another enzymatic approach is the multi-enzymatic synthesis of lactic acid, and the results are obtained from Universidad Autónoma de Barcelona. So in this part of the BIOCON-CO2 project, a multi-enzymatic route was used for the conversion of industrial carbon dioxide towards lactic acid. And this can be used as feed additive or, for example, to produce polylactic acid, a biodegradable polymer. This multi-enzymatic assay involves an internal cofactor regeneration loop. and it is processed by different enzymatic steps. So the first would be the synthesis of pyruvic acid from carbon dioxide and acetaldehyde via the pyruvate decarboxylase. And then the pyruvic acid is reduced to lactic acid via the lactate dehydrogenase using NADH as cofactor. And this cofactor can then be regenerated in the oxidation step of ethanol towards acetaldehyde via the alcohol dehydrogenase. Yeah, and here are the results which were obtained when performing the assay with synthetic gases mimicking real-off gases. So in this case, it was the composition of blast furnace gas, which has relatively high amount of carbon dioxide and carbon monoxide and low amounts of oxygen and hydrogen. Yeah, and during the project, the enzyme amounts were optimized, and so in the end, about 52.4 micromolar of lactic acid could be achieved after 96 hours. And yeah, this is a 6.5-fold increase when compared to the state of the art at the beginning of the project. And also, when using 100% of carbon dioxide instead of the concentration used in the or present in the blast furnace gas, a similar amount of lactic acid could be produced, and this means that no additional enrichment of carbon dioxide is needed when this assay is used. So, and these are the results so far. Yeah, thank you for your attention.
Thank you, Gabriele, for the nice overview, very complete, and also showing not only your own results, but the results of all the microbial cell factories. Are there any questions? I see one in the back.
Yeah, I have a question about the first presentation, the first part. You showed that when you use the plasmid, you had a lower amount of protein, like a lower expression. Is it because you're not using selection and you're using the plasmid, or you are using selection?
It was with
antibiotic.
I showed the comparison between the two strains, and it was with selection marker.
Okay.
So actually, I'm not sure. In the first place, I would have expected it other way around.
Yeah.
Because you have usually, at least in E. coli, you have origins of replication which allow that you have multiple plasmids in the cell, and so you have a higher copy number which can be used.
Yeah, that's what I was thinking as well.
Yeah, but it was different. So maybe it is a specific burden for the cell to produce the enzymes. Yeah.
Is the growth worse when it's carrying the plasmid as well? Did you reach lower OD values?
Let's take a look. I think it was rather similar, but it can be that it was a little bit lower.
Okay.
Yeah, are there any other questions? Oh yeah, Aline and then Marcel.
Thank you. Yes, I just have a question to this slide as well. So, and your following experiments, which gas composition did you use here in these experiments?
This was as well 20% of carbon dioxide and 80% of hydrogen.
So basically all of your experiments were like just on
almost,
these?
At least these which are shown here.
Thank you.
First of all, thanks for this interesting overview of different technologies. One question concerning the electrofermentation. You mentioned it's an anaerobic process. At the same time, you've got electrolysis and you produce hydrogen. I guess you produce oxygen as well. Does the oxygen influence the process? Does it inhibit the process?
I would like to hand over the question
to Daniele.
Okay. Do you want to put the slide with the photo? It is a two-chamber reactor, and the part of water splitting is happening in the anode chamber, but in this case, I don't know if you can realize it.
Is the one with the culture, and here's
yes.
the one with.
Exactly. So there is a membrane in the middle that is not permeable to gases, and the oxygen is vented, and it will not affect the fermentation in the other chamber.
Okay. So, is there any other question more? Okay.
Maybe another question to you, Anna. So the process you established with gas fermentation first and then a glucose fermentation the second step.
Yeah.
In the final products, do you know the ratio of carbon coming from gas towards the ratio of carbon coming from glucose?
Yeah, what we did is first produce acetate from CO2 using the acetogen, and then we switch off the gas and we inoculate it with the solventogen and we added glucose. So in these conditions, the acetogen is not growing anymore. So all the products we get after the switch, they will be only from the solventogen. So what we wanted to test is if we could co-utilize acetate and sugar.
Okay.
And that is what we observed.
Okay.
Yeah, but in these conditions we knew which product was coming from which organism. When you do this simultaneously, then it's more difficult. But we showed that you can co-utilize it. Yeah.
Did you measure the acetate amount during the second fermentation?
Yes.
And it's
we saw only decrease.
Perfect.
We didn't see increase. We saw decrease, and we have also done this experiment in a continuous mode with both organisms, and we can see that is co-utilized with sugar or also with organic acids. But yeah. Okay, so we continue. Maybe we can go on because otherwise we are in time.
It's just
notes.
something. There's a question from the online audience, so just a really last one, and as you say, Anna, we'll just. Paolo Costa is asking how do you decide on the hydrogen CO2 ratio? Is it fixed or it depends on the microorganism, the end product, or something else?
We tested different compositions of hydrogen and carbon dioxide, and we recognized that the best growth occurs at 33% of carbon monoxide, carbon dioxide, and hydrogen each. The aim of the project was the utilization of carbon dioxide, and when the cells have the chance to use carbon monoxide, they use it and produce carbon dioxide. So we restricted the availability, and we also compared different ratios. So 80% of hydrogen and 20% of carbon dioxide, and vice versa. And logically, they preferred the composition that we finally chose. And from thermodynamic and calculating approach, it makes sense because they need a lot of energy to do this, and they need a lot of reducing power to reduce. Because the butanol and hexanol are quite reduced molecules. So that's how we came up with this composition.
Perfect. Thank you so much, Gabriele.
Thank you. So we move on to the next speaker. So we welcome now Aline Husser. She's graduated at the Technical University of Dortmund, and she's performing her PhD research, and she's being supervised by Professor Jochen Buchs. And she will show today the results on the strategies to increase the CO2 solubility so it can be used more efficiently in fermentations or in other reactions. And yeah, she has performed almost your whole PhD in this project, and you are almost finished now. So that's nice to see. So please go ahead.
Thank you, Anna, for the nice introduction. And welcome everyone again. And I'm happy to give you the overview of the strategies for to improve CO2 solubility within the BIOCON-CO2 project. So just another brief overview about the project. Scientifically, the project was divided into 3 stages, looking at stage 1, the CO2 solubilization strategies, stage 2, bioprocess development, and stage 3, downstream technologies. So each of these 3 stages are the topic of these afternoon sessions, and I will focus on giving you an update on the experiments and the results we've performed within the project regarding the CO2 solubilization strategies, mainly focusing on the 3 strategies we see down here, which is 1, the use of carbonic anhydrases, the use of a trickle bed reactor, and the investigation of different process parameters by process optimization using the SynRamos, which I will explain later on. All of these solubilization strategies were mainly focused on one of those bioprocess developments Gabriele already told us about, but there will also be applicable if we see some results through all those biocatalytic processes we see here. So let's start with the use of carbonic anhydrases, which was performed by our partners at Leitat. So carbonic anhydrases are here used as a tool to increase the absorption of CO2 into the liquid. And the main benefit of carbonic anhydrases is that these are enzymes which have the capability to convert CO2 into bicarbonate at a really, really high turnover rate. So it makes it really applicable for processes which are really high and limited to a gas-liquid mass transfer. Besides the high turnover rate of the carbonic anhydrases, they also offer advantages as mild operating conditions, but also as most of biocatalytic systems, they have some disadvantages. In this case, mainly due to inhibition by sulfur-containing species in the off-gases, as we already heard earlier before, the death valley of gas, and a low stability over time. So, in the beginning, to look at the carbonic anhydrases, the main focus was to identify really active species of these ones. And the one we started within in this project was the human carbonic anhydrase, which was really promising in this kind of state to be really active. And we tried commercial ones and the recombinant ones, and testing them, they showed mainly the main stability over time. And regarding the cost factor, all experiments you've seen here were performed with the recombinant strains produced by Leitat itself. Going a little bit deeper into the stability measurement, on the top left, we see these stability testing over 15 days using the recombinant human carbonic anhydrase, stored at one's room temperature in the line in blue and at 4 degrees. And impressively, we do not see any difference between those storage conditions, which is quite nice for a long-term stability. But we do also see a pretty steep decrease in activity during the first day with both enzymes they're used. Additionally, Leitat performed tests regarding the impurities which could be in the gas streams and the effect of those impurities on the activity of the enzymes. And here shown just the results for the impurity which are sulfur containing, which had like the biggest impact on the enzymes. And these results also correlated with the literature, what is known in the literature, and about the enzyme activity. And one way to address and increase the enzyme stability would be through targeted mutagenesis. And therefore, partners at RUC and Leitat performed experiments regarding targeted mutagenesis or directed evolution through to computational strategy to increase the enzyme stability. So at the first point, they had to perform a target selection. Therefore, they used the enzymatic system which was used in work package 5, and then started using a Fresco protocol, developing a 3D structure of the carbonic anhydrase. And then the computational steps followed by investigating the disulfide discovery, so the active sites in the enzyme, which can be targeted by directed mutagenesis, and afterwards following by energetic modulations. So after performing this computational strategy, 755 screen mutations, possibly stable mutations could be selected. And after selecting further, 49 mutations were selected. And after looking into it more deeply, only 8 of them were transferred to later for targeted mutagenesis, and also the 21 primer sets to perform these directed mutagenesis were also being transverted to later. At later, they performed the directed mutagenesis and cultivated all their enzymes there. And what we see here is just the best mutant out of the 8, which they tested in this experimental setup for the solubilization, where we had like 2 jacketed trickle bed reactors, and there we could flush them with CO2 and measure over time how much CO2 would also be diluted into the buffered medium. And what we see here on the right is that one of the mutants displayed a higher activity, about 1.5-fold compared to the human carbonic anhydrase in the wild type. And it shows a higher CO2 solubilization with a maximum of 30% after 20 minutes, which was quite nice to get like really beneficial results out of the directed mutagenesis. Looking at the second strategy we investigated was the trickle bed reactor. So what is the trickle bed reactor? A trickle bed reactor is a chemical reactor that uses the downward movement of a liquid and the downward or upward countercurrent movement of gas over a packed particles catalyst. The trickle bed reactor was mainly designed to be used in the Arabic fermentation using Cuprivatus necator, and the critical parameters for the use in anaerobic gas fermentation would be the ability for bacteria to be adhesive to the packed material, to the catalyst within this reactor. And of course, the adaptability of the packing material inside the reactor, and a possible degradation suffered by of the packaged material suffered by the counter-flowing streams within the reactor. So one main part of the investigation was the investigation of the packaging material within this system, and the aim therefore was to study innovative and environmentally friendly packaging material, which could be then reused and be beneficial for waste management and use like environmental friendly packaging materials. So what were investigated were polyurethane foams, fibrous materials, hardwood chips, and polypropylene pellets. And from all of the materials that were tested, the non-woven and 3D fibrous materials, the PES textiles, have proven to be the best materials for bioadhesion and growth of the bacteria in this case. So to conclude, for the trickle bed reactor within the BIOCON-CO2 project, it could be demonstrated that the viability of the TBR used in CO2 capture using Cuprivatus necator has been proven. 10 different packaging materials have been evaluated. It was determined that the capability of the packing materials to create biofilms by C. necator was also possible. And further, there was plasma treating on the selected textiles, which were proven to be the best ones, and to further increase the productivity and the overall process for these ones. And we're hoping to see some of publications about these topics soon. Looking into the third optimization CO2 solubilization strategy would be like looking into process parameters and optimizing them to perform gas fermentation. And to optimize process parameters for syngas fermentation, you would have to first look on the characteristic of syngas fermentations for CO2 utilization. Mainly with our focus was with Clostridium lungdali, which Gabriele showed us earlier. So the main constraint, or one of the main constraints, is the low substrate solubility for carbon monoxide and hydrogen. We're always talking about CO2, of course, but compared to CO2, hydrogen is much lower soluble in the medium. And looking at the specific organism, Clostridium lungdali, we're looking at the CO2 conversion, which is always dependent on additional hydrogen, as we heard earlier before. And while we have CO, carbon monoxide, present in most of the off-stream gases, using this organism, the bioconversion of carbon monoxide is even more energetically preferred over the use of carbon dioxide. So in the worst case, we're using off-stream gases. We want to reuse carbon dioxide, but instead we are consume carbon monoxide and will end up in producing more CO2. So in order to get a good understanding and to be able to perform some process optimization, two parameters are critical: that we have a continuous gas supply for sufficient growth, and to look at the further on the scale up, since in real industrial environments we also have a continuous gas supply, and of course the monitoring of CO2 consumption if you want to look at the CO2 conversion, since we have this system over here. So looking at the state of the art of process development for gas fermentation, we mainly see two systems right now. We see the serum bottle and the fermenter on the other hand. The serum bottle has no online monitoring, so we don't know what's happening right there. We have a limited gas supply just within the headspace of the serum bottle, but beneficial, we have a high throughput. The systems are easily to use. We can produce a lot of serum bottles simultaneously. And on the other hand, we have the fermenter. With the fermenter, we have online monitoring. We have a continuous gas supply, but preparing a fermentation, all of the fellow colleagues know that it takes a lot of effort to get a fermenter running and then running it for days. So we are really highly limited in throughput. Therefore, we at our chair were thinking about, isn't there something to fill the gap? And therefore, we introduce the gas shaker, or SynRamos, which is a device for online monitoring. So we can have online monitoring, we have a continuous gas supply and a high throughput. And now I will show you a little bit more. So the SynRamos is a device for gas fermentation in shake flask. With it is it possible to cultivate on gaseous carbon sources in up to 8 parallel shake flasks with an individual adjustable gas composition, just as you like, taking all these gases you see there on the left. And it's also used to save with toxic and explosive gases. And the measurement principle is based on measuring the pressure in the headspace in each flask and the measurement of CO2 partial pressure via high-range gas sensors. Going into this a little bit more deeply, what happens in the shake flask? So looking at gas fermentation, we have mainly the three gases: carbon monoxide, hydrogen, and carbon dioxide. Carbon monoxide would be consumed, hydrogen would be consumed, and carbon dioxide, depending on the process which we are reaching, is either produced or consumed. So measuring the gross gas transfer rate would be like the overall consumption and production of gas, and which is measured via pressure sensor, and the carbon dioxide transfer rate, the COTR, is measured via CO2 sensor, also in the headspace of these flasks. In detail, the setup looks like this. We have a flask, we have an inlet and an outlet valve, and a pump which is flowing the gases from the inside of the shake flask over the sensors we used. So basically our measurement method, the measurement principle, is based on two phases. In this system we have a flush phase and a measurement phase. During the flush phase, the system is continually flushed with gases. Both flasks are, ventiles are open, and organism has enough gas to grow. Going into the measurement phase, we close both valves on the shake flask, and we can see a decrease in the carbon monoxide concentration, and which represents just the activity of the microbial organisms. So this would be like the overall pressure loss of carbon dioxide. Then going again in the flush phase and performing a measurement phase afterwards. Just as I said, depending on the gases which are consumed by the microorganisms, in this case just consuming carbon monoxide, also carbon dioxide is produced. And this we see here in the green line. During the measurement phase, consuming carbon monoxide, carbon dioxide partial pressure goes up. So the gross gas transfer rate you see here is just the sum of all independent partial pressures of these gases looking over time, just to keep it in mind if I show you the results of our case study in a minute. And further, the carbon dioxide transfer rate is directly measured by a carbon dioxide sensor, which represents the consumption or production of carbon dioxide. Looking at a case study for gas fermentation using Clostridium lungdali, we performed an investigation of different gas transfer rates, and there looked at the effect of gas composition and carbon monoxide conversion, and at a look on the enhanced product formation, mainly focused on ethanol production. To investigate different gas transfer rate, we performed a stepwise increase of the shaking frequency during the cultivation, and a higher shaking frequency results ultimately in shake flask in a higher gas transfer rate. So what we do see here now is the graph I will show you. At the top we will see the products, in the middle the gross gas transfer rate, and at the bottom the CO2 transfer rate. Just looking at the offline measured products, in this case acetate, we do see an increase over time and with the increasing shaking frequency up to 300 RPM. At 300 RPM, the organism stops producing acetate, which indicates some kind of like a metabolic shift in the system at 300 RPM. And further looking at the ethanol production, we see nearly no ethanol production at lower gas transfer rate, but an increase in ethanol production with an increase in gas transfer rate, which reaching the highest production rate just with the highest gas transfer rate and ending at about 15 grams per liter after 130 hours. But for now, we don't know what's happening with the gas in the system. So we look at the gross gas transfer rate. And what we do see here is that the gas consumption as well increases with the steps of increasing shaking frequency, as we would consider, since more gas is there for the organisms, is highly likely to be limited in some kind of like a gas liquid mass transfer. But quite interestingly, reaching the 300 RPM, the gross gas transfer rate rapidly drops. And looking at the CO2 transfer rate overall, we might get an idea what's happening after 300 RPM. So for the first two shaking frequency, we're just round about a net zero CO2, which means we do not overly consume CO2, but we do not also produce CO2. So with the hydrogen in the system, we're on a net zero value, which is better than producing more. But after the shift to 300 RPM, we do see a steep increase as well in the CO2 production. So here keep in mind, gas consumption is negative and production is positive. So this is a CO2 production we see in the system. And this indicates that at some higher gas transfer rates, the organism might likely be limited from kind of the carbon monoxide concentration. And in this case, the increasing gas transfer is likely lead to hydrogenase inhibition within the Clostridium lungdali. So overall, to summarize this, the gas shaker is a novel shake flask system for online monitoring of gas transfer rate and is applicable for process development. And analyzing gas transfer rates will give us a deeper insight into the small-scale gas fermentation processes and mainly increase the throughput if some more variants will be coming our way soon. And therefore, I thank you for your attention, and I'm open for questions.
Thank you very much. Are there any questions in the public? Oh, Despina.
Have you managed to run it in steady state? And if so, what was the behavior of the system? What was the gas transfer rate?
What do you mean with steady state in this case? So like
For
just being
period.
so this
like,
is
like at the last stage where you had for so many hours, it looked like it reached steady state pretty much.
It's kind of a little bit difficult looking at the shake flask, since it's not a continuous fermentation based on the liquid part. So we do have a continuous gas supply for the carbon and energy source by floating it with gas. But looking just at the liquid, it's kind of like still a batch process. So you cannot really talk about steady state like in a continuous fermentation point of view. But what we do see, do you know the slide, maybe 25 or something? Oh, I wanted to go on 25, but it didn't work. So what we do see here with the limitations regarding the different RPMs is most likely due to a gas-liquid mass transfer. So being at one shaking frequency and being limited, in this case, by carbon monoxide mainly, it's kind of like an, gaseous steady state-ish, but it's basically just on the gas-liquid mass transfer side.
Are there more questions? I have a question. I know that you have been working on pressurized systems as well during the project. How could you combine these measurements also on pressurized systems, or?
Yes, of course. So basically, when you look at gas-liquid mass transfer rates, you have two effects on the microorganism. One is the effect of how much gas they see, and basically by increasing or investigating different gas-liquid mass transfer rate, you can also perform a scale-up to reach like the same gas-liquid mass transfer rate in a reactor by increasing the pressure, for example, and not by increasing the stirring rate. Yeah. This could be one point, and the other part where the Synrammers is, from my point of view, mainly applicable is in screening. So you get like a bunch of organisms you want to screen, you want to test with different gas compositions, and you want to test some different effects. You screen them prior in this device, and then you scale up. But you also, of course, get an idea about what gas-liquid mass transfer, if you are limited or if you're not limited.
Okay, and did you find the same, because you can see very nicely that when you increase the stirring, you increase ethanol production. Do you observe that with CO2 or with CO as substrate? Is it always the same, or is it specific for these conditions?
It depends. So the overall trend is always the same. So what we did tested, we tested different gas compositions. We tested low amounts of hydrogen and higher amounts of hydrogen, and we tested different pH values as well. And what we do see is the overall trend that ethanol production increases with higher shaking shaking frequencies. So sorry. We do see the strand which is mainly due to the stress which is caused to the organisms, as you know as well. Clostridium mingali, if it's really working good, it mainly will produce acetate because it's more beneficial for the organism itself, but it will produce alcohol more likely under kind of like stressed conditions. And the key is to find a stable stress condition where the organism will produce the mass.
And these results, they are already published for some part, or?
No, they're not yet published, but they will be published pretty soon, since I'm in my final part. So they will definitely going to be published about the screening we did there.
Okay, thanks again, and we will go to our online speaker for this session. That is Thomas. Hi, Thomas. Can you see us or can you hear us?
Yes. Good afternoon.
Okay.
We can't hear you.
Can you hear me?
We cannot hear you.
Maybe you may be muted. Can it be?
Maybe you are muted.
No. Can you hear me?
Yes. Yes.
Okay. Now I will make an introduction. Tomás Roncal, he's a researcher at the Tecnalia Institute in Spain. He works at the group Sustainable Chemistry of the unit Energy, Climate and Urban Transition. In this institute, he has a PhD in biochemistry from the University of Basque Country in Spain, and he's working on production of bioproducts through fermentation and biocatalysis, also focusing on downstream processing of the products. In the BIOCON-CO2 project, he has coordinated the work package 6 on the downstream and validation of the products.
and he is involved himself on the task on the downstream processing of the formic acid produced. So, yeah, you can start, Thomas.
Thank you, Anna, for the introduction. Will you hear me?
Yes, yes, we do hear you.
Okay, thank you. Well, my presentation will be about technologies and tools for downstream processing, and mainly focus on the work carried out in the BIOCON-CO2 project. First, my base products must be efficiently recovered and purified from the media where they are produced to be used in the final applications. So, product recovery and purification from bioprocess media, known as downstream processing, is often a complex task accounting for a significant share of the process cost, up to 75%, mainly due to the relatively low concentrations of the target molecules and the matrix complexity. This is of special relevance for CO2 derived products that usually are present at 1 to 2 orders of magnitude lower than, for example, their sugar derived counterparts. Therefore, the development of efficient and cost-effective downstream processes for product recovery and purification is a mandatory need for industrial feasibility, and accordingly, efficient and non-energy intensive downstream process technologies are preferred. In the framework of the BIOCON-CO2 project, Work Package 6 is focused on the downstream processing and validation of the products obtained in the different microbial cell factories. There are two main objectives in this work package. Develop downstream strategies applicable to the target molecules that are C3 to C6 alcohols, PHB, and lactic and formic acids, taking into account the characteristics of the effluents obtained in the processes where they are produced. And second, validate the purified products obtained from downstream by the end users, both physicochemically and in their main market applications. In this presentation, we will only explain the tasks related to the downstream processing. We have more detailed description of the process developed for one of the target products, the formic acid. First, during this project, a design of experiments tool for design and assessment of downstream separation routes has been developed by Ghent. This tool is user-friendly, works with up to 4 different variables using response surface methodology, and has the capability of looking for optimal conditions. It is open source and should be available in Senova, an open source platform, as you can see in the slide, the link. Even though it is user-friendly, a tutorial has been made. And finally, it has been validated against a design of experiments commercial software like Design Experiment. Second, the task related to the downstream of alcohols to recover them from the Clostridium unduli effluent was carried out by Pervatex using evaporation. This first step was to determine the optimal process parameters using an artificial medium based on the effluent composition at that time. The process performance was measured through the recovery efficiency, which is the percentage of alcohols recovered from the effluent. The first process parameter optimized was the feed temperature. As shown in the left figure, an increase in feed temperature resulted in increases of the percentage of recovered alcohols. The highest recovery efficiency was found at 70 degrees, which is also the temperature limit for the membrane. The second parameter optimized was the permeate pressure. As shown in the right figure, decreasing the permeate pressure resulted in a higher recovery efficiency. Both an increase in temperature and a decrease in permeate pressure led to an increased driving force across the membrane. That explains the higher recovery efficiencies. The optimized parameters that were chosen were a feed temperature of 70 degrees and a permeate pressure of 20 millibar. The last step in this task was to verify the result with real effluents obtained from BBEPP. Furthermore, the goal was to obtain a permeate with a butanol concentration above 400 millimolar. To reach this goal, 3 extractions were needed, as can be seen in this scheme. The permeate from the first extraction was used as the feed in the second. Due to the limited availability of real effluent, an artificial medium was used for the second and third extractions. After 3 extractions, more than 90% of the butanol from the effluent was recovered, reaching a final concentration of butanol close to 500 millimolar from a starting concentration of only 1 millimolar. The next task was that related to the downstream of PHB and lactic acid, and was carried out by INTAS. For the PHB downstream, the feed source are cells produced within the project, which contain around 80% in mass of PHB as a high purity intracellular product. The process consists of breaking the cells with sodium hypochlorite, controlling the exposure of PHB to this chemical. Then a centrifugation with several water washes, since it is not soluble in water. And finally, an acetone wash to recover it as a dry powder. PHB downstream achieved high purity, more than 90%, and a high recovery, up to 92%. The other task was the downstream of lactic acid. It is produced in a biocatalytic reaction. Since the expected lactic acid concentration in the feed are not yet achieved, downstream experiments were done with a synthetic effluent based on the real one, but not with lactic acid. The separation is based on a membrane filtration cascade of ultrafiltration, nanofiltration, and reverse osmosis. Ultrafiltration retentate contain biomass and enzymes that might be recycled to the process. Nanofiltration aimed for the rejection of medium-sized molecules like sugars and proteins. The rejection of lactic acid was around 50%, much higher than expected, which means that a lot of product will be lost if high purity is required. Last step was a low rejection reverse osmosis. It presented a good recovery of lactic acid, greater than 99%. However, the presence of ethanol associated used by a catalytic reaction reduced its purity. Overall, concentrations of lactic acid close to 3 grams per liter were achieved. And then the final target product in the project was formic acid. And the task related to this downstream processing was carried out by Technarians. The process for formic acid production from CO2 carried out by another project partner, by Ghent, is a 2-enzyme coupled biocatalytic reaction involving enzymes formate the hydrogenase, LPH, to catalyze the reduction of CO2 to formic acid, and glucose the hydrogenase, GDH, to regenerate LPH by oxidation of glucose to gluconic acid. So, the formic acid effluents obtained were characterized by a rather low concentration of formic acid and the presence of a picomolar concentration of formic and gluconic acid. This is the co-product, with the composition shown in the table shown in the slide. So, according to the effluent composition, it was proposed a downstream strategy using 2 successive separation technologies, nanofiltration and reactive liquid extraction. The objective of the first step was to separate formic and gluconic acids by nanofiltration using commercial membranes with the lowest molecular weight cutoff available, between 150 and 300 Dalton, taking into account the quite different molecular weights of both acids. After this nanofiltration step, the idea was to concentrate the formic acid from that gluconic acid depleted solution by a reactive liquid extraction process, using a tertiary amine as extractant and an invisible organic solvent. The work done in this task, this project, it was published, and you can see the reference at the bottom of the slide. Regarding the first step of nanofiltration, a scheme of this process is shown in the slide. The whole process is composed of 3 nanofiltration steps that can be separated into 2 divergent laps. One leading to an essentially pure formic acid fraction, the permeate 2, and the other leading to an almost pure gluconic acid fraction, the retentate 3. The first one involves the successive nanofiltration of the feed, nanofiltration 1, and the permeate 1, nanofiltration 2, to obtain permeate 2, and accordingly can be named permeate acid. The second one, in turn, involves the successive nanofiltration of the feed, again nanofiltration 1, and the retentate 1, nanofiltration 3, to obtain retentate 3, and accordingly can be named retentate pathway. In this slide, we can see the separation progress through the permeate pathway. Starting from a synthetic effluent presenting the expected composition of the biocatalytic process, that is 1.8 grams per liter formic acid and 9 grams per liter of gluconic acid, following every nanofiltration, the concentration of gluconic acid in the permeates was considerably reduced, without minor decrease for formic acid. The final permeate contained formic acid almost pure, with more than 99.6% purity and 1.37 grams per liter of concentration and a yield of 47.6%, with less than 0.01 grams per liter of gluconic acid. Going with nanofiltration, we can see here the progress through the retentate pathway. Gluconic acid was really concentrated in the retentates, with little variation for formic acid related to the feed, as shown in this slide, where the separation progress to the retentate pathway is depicted. The final retentate was an essentially pure concentrated solution of gluconic acid with 99.4% purity, a concentration of 102 grams, at a yield of 77.2%. So, following the final nanofiltration steps, 2 main fractions were obtained. The permeate 2 enriched in formic acid, and the retentate 3 enriched in gluconic acid. The other 2 fractions, retentate 2 and permeate 3, will be recycled to the starting feeding to increase the separation yields. Retentate 3, that is a fraction rich in gluconic acid, was not further treated and was considered a gluconic acid pure concentrated solution. Permeate 2, in turn, although was basically formic acid pure, was rather diluted and had to be concentrated. So, permeate 2 followed a second step of reactive liquid extraction to concentrate it. Regarding the process of reactive extraction, first we tested the extraction performance of 3 amine-type extractants: triethylamine, TOA, dicyclohexylmethylamine, DCMA, and diethylamine, DOA, and 3 diluents: N-octanol, methyl-isobutyl ketone, NPK, and toluene. The most efficient combination was DOA and octanol, which resulted in an extraction yield of 97% and a distribution coefficient of 34. The distribution coefficient is the concentration ratio of the solute between the organic and the aqueous phases. The final stage in the reactive extraction process involves the re-extraction of back extraction of the solute from the organic phase to recover the extractant-free solute in a new aqueous phase, and simultaneously to regenerate the extractant for reuse. Among the different methods to perform back extraction, treatment with aqueous-based solution was selected. And of the 3 bases tested, sodium hydroxide, sodium bicarbonate, and sodium carbonate, the best results were obtained with sodium hydroxide. In this slide, we can see the final optimized process. Both the extraction and the re-extraction processes were performed in 2 times, with a 10-fold volume decrease in each step, under the conditions shown in the table. A final solution was then obtained with a formic acid concentration of 174.5 grams per liter, which is 78 times more concentrated than the original feed. The total recovery yield of formic acid in the reactive extraction step was 78%, although probably it could reach 90% taking into account adjustments related to the water co-extraction circuit. In addition, the extractant diluent mixture of EOA and N-ethanol was found to maintain its functionality when recovered after use, so allowing to be successfully reused in additional reactive liquid extraction cycles. Finally, as conclusions, we can say that a design of experiments-based tool for design and assessment of downstream has been developed, and efficient downstream processes for the target product have been developed. For alcohols using preparation, for PHB by means of cell lysis and separation of the insoluble solid, for lactic acid by means of ultra nanofiltration and reverse osmosis, and for formic acid by using nanofiltration and reactive liquid extraction. Thank you very much for your attention.
Thank you. Are there any questions from the audience? Yeah, I do have a question. Oh yeah, first Aline.
Thank you for this presentation. Just as I'm not really a specialist in downstream processing, so the overall process you showed us, how would you describe?
I can't understand this. The sound is very bad.
Yeah.
Is maybe this microphone on as well?
Is it on?
Oh.
Can you take it?
Yeah.
But he said he muted it. Can you hear me now better?
Yes.
Yeah.
Okay, perfect. Yes. Thank you. So just in terms of costs regarding this this downstream process you showed, would you rather say it is like a very cost intensive, low cost, or just in a medium range, just to give us an overview?
Yes, thank you for the question. Yes, this is a question that usually appears in these processes. Our intention was not at this point of the project to make an economic evaluation of the process, but simply to prove that it was technologically possible. So I cannot really answer your question regarding this economic evaluation, but we expect that taking into account that the technologies used are not energy intensive, and they are expected to not be very, very cost.
Okay. Yeah. I have a question, because I have seen that in the formic acid production we also have gluconic acid production, and for the lactic acid we also have another co-product. When you have these two products, is it a disadvantage for the purification, or it doesn't necessarily be a disadvantage because you will have two products? How do you look into that, Thomas?
Yes. Well, in this case, taking into account that our processes were biocatalytic, so that means that the effluents were very simple. So the purification does not complicate more a lot. It is very different when the effluents are fermentation media, where there are a lot of ingredients, a lot of products in that. So in that cases, it is very much. It is not as easy to do the purification. In this case, we had two products, formic and gluconic acid, and the separation. I'm sorry. We could use the the advantage that both molecules are very different in size, in molecular weight. So this can use, this allows us to use that nanofiltration step to separate almost perfectly both products. For other products, like in the case of lactic acid and ethanol, probably with unstable nanofiltration, the separation, as shown in the work carried out by Lectat, the separation of both products was not good using that technologies of nanofiltration, reverse osmosis. But as one product is an acid and the other is an alcohol, another technology, different technologies can be used that would improve that separation.
Okay, thank you. Are there more questions or comments? Then thanks again, Thomas. So we will go to the coffee break. The next speaker is Dr. Helene de Wever. She has a PhD in Applied Biological Sciences and works at the Flemish Institute for Technological Research, VITO, and she works in the business unit of Separation and Conversion Technology. She is currently focusing on two research lines. The first one is bioprocessing intensification. That means a combination of separation technology and bioconversions in order to get more efficient processes with higher cell density, for example, or selective product recovery. The second line is the valorization of CO2, rich gases, and C1 feedstocks using biotechnology. So it fits very well with our project. She has coordinated the BioRecover European project that is a kind of twin project of BIOCON-CO2. So please go ahead.
Thank you, Anna, for that kind introduction. And thank you to the organizers for inviting me to present the BioRecover project. Of course, I also want to acknowledge at the start the other project partners who have contributed in many different ways to the results and the activities in the project. I will only give some highlights today. I cannot acknowledge everything or present everything that the various partners have done. So let's go. In the overarching, under the umbrella of carbon capture and utilization, the BioRecover project fits very nicely because it's focused on biological routes for CO2 conversion into chemical building blocks. I want to give a few important messages at the start. In our project, we only focused on CO2 as a gaseous feedstock, so not on CO, only CO2. It was a research project, so we've done work at lab scale, basically, trying to reach TRL 5, but not beyond that. And in our consortium, we had 8 out of 12 industrial partners, which means that, unfortunately, I cannot communicate a lot on the results, but I will give you highlights and a flavor of the various types of activities we did and some of the outcomes there. Maybe first, why do we want to look into biotechnology for CO2 conversion, and how does it compare to chemocatalytic processes? Well, there is a number of advantages linked to biotechnology. For instance, that we have a self-reproducing catalyst, that reactions take place in milder ambient conditions, which may come with advantages for safety and sustainability. Usually we have a high selectivity in the conversion, or much higher than when we have a chemocatalytic conversion. And also, typically, the microorganisms have a quite high tolerance for impurities or for other types of impurities in gases and for variations in gas composition. However, we also have some disadvantages, of course. I think we've heard already some productivities, titers are low or lower than what we see in other fermentation processes, and certainly when we compare to chemocatalytic conversions, there is sensitivity to the product. We have to deal with product toxicity, and we have finally usually a product in an aqueous medium, which comes then with a lot of challenges in terms of the downstream processing. Still, we want to investigate the potential of biotechnology. You did for a number of routes, we did for a number of other routes and sectors here. I will go step by step through the scheme with the various activities that we did, and I want to start first on the CO2 emissions. The two sectors that we were focusing on were, on the one hand, the cement industry, with CO2 emissions, of course, and on the other hand, petrochemistry and refinery. And the first thing that we tried to do was to characterize the emissions and the main sources of emissions, for instance, in the refinery and petrochemical sector. And then you see here an overview of the kind of emissions we can expect per million ton of crude oil, where we have, of course, major emissions of CO2, a number of other impurities that are present there. But basically, most of the CO2 emissions in petrochemistry are linked to energy-producing processes. And then you see there heaters, furnaces, gas turbines, and so on, contributing quite a lot to the CO2 emissions. Depending on the complexity of the petrochemical plants, there is a variety of sources, and the main ones are crude distillation unit, hydrogen production unit, and fluid catalytic cracking, with a variety in CO2 concentrations, purity, and other impurities present. So this is the kind of inventory work that we started with for the various sectors that we were interested in. The second thing is then to look whether or not a CO2 concentration step is needed. And in some cases that is needed, because the CO2 concentration is as low, for instance, as 10–50%. And then we want to look into ways to enrich and purify the CO2 from the emission stream. So on the CO2 capture step, Luleå University was the partner who investigated a novel approach for a chemoenzymatic hybrid approach to capture CO2 and to enrich it. The reference situation is the use of monoethanolamine, so an amine that is typically used to capture and sorb at a very high rate CO2 from flue gas emissions, for instance. But it comes with the disadvantage that you need very high temperatures to regenerate it and to release the CO2. So as an alternative, you could look for different types of solvents that allow for a regeneration at a lower temperature, but then they usually come with decreased capture rates. So the idea here was to look into a novel hybrid solvent, a combination of an amino acid ionic, wow, that's a bit strange with the pointer, an amino acid ionic liquid blend, and to further increase the capture rates for CO2 by adding an ultra-stable carbonic anhydrase enzyme to it. So in our case, we use the carbonic anhydrase enzyme in combination with a novel hybrid solvent to improve capture of CO2 from emissions. The way to go was to start from an ultra-stable enzyme that was already compatible with temperature ranges up to 60, 80, even 100 degrees, but then to further look for variants and to apply mutations and to find variants that would be more compatible with the typical impurities that are present in flue gases and that can be inhibitors for downstream reactions and conversions. The main ones that we investigated here were NOx and SOx, and actually a number of mutant enzymes were obtained that showed a 50% increase in resistance to these flue gas inhibitors. In a subsequent step, the focus was on finding a different hybrid solvent mixture, which allowed to come with competitive sorption and desorption properties. And this is then this combination of an amino acid ionic liquid and a tertiary amine that in a blend led both to high initial sorption rates and also high regeneration at the reduced temperature that we were interested in. So this would allow for a more energy efficient or less energy intensive capture of CO2 and regeneration of the concentrated stream. Finally, a pilot scale rig or a system was developed and also tested with this novel hybrid solvent in combination with the enzyme on real off-gases to demonstrate that CO2 absorption and desorption can be performed at competitive conditions. So this is a few words on the CO2 capture and pretreatment work that was done. So after looking into the needs and a potential alternative solution for the CO2 concentration and purification step, we then go to the actual conversion of CO2 through a variety of processes. So first we looked into 3 microbial platforms. You see the 2 autotrophic ones, which are well known, I would say, Clostridia and Cupria viridis strain, which were investigated by Global Bioenergies for production of isobutene and by Enobrac for production of lactate. In addition to that, we also had a capnophilic platform of Thermotoga neapolitana, which is hyperthermophilic, so it's active at 80 degrees, strictly anaerobic, and actually produces lactate in combination with hydrogen. Capnophilic means CO2 requiring. So it's not purely based on CO2, it's a combination of an organic source with CO2. CO2 combines with acetyl coenzyme A somewhere in the metabolism to produce lactate. So this is a nice alternative platform to fix CO2. With external CO2, lactate production can be improved to fix CO2 in lactate in combination with hydrogen generation. Why did we pick these three different platforms? Well, on the one hand, because there was a difference in oxygen tolerance. We know a lot of flue gases contain a lot of oxygen, so we certainly wanted to have also an aerobic platform. And we have the ranges in temperature going from 37 up to 80 degrees, and I will come back to that later on. In summary, on the microbial platforms, a manipulation and genetic toolbox was established to genetically access Clostridium lugdalii, and the full isobutene pathway was implemented in the organism, and isobutene production also demonstrated and achieved under autotrophic conditions. For the Cupria viridis strain, there was an issue with lactate reconsumption. We focused at, or we aimed at lactate production from CO2. Some lactate reconsumption was observed, and this had to be solved. And lactate production could then also be improved in that way by overexpressing lactate dehydrogenase. The approach here was patented by the company. And then on the Thermotoga platform, substantial work was done to increase productivities and also to establish the genetic tools, because particularly when you go to the thermophilic, hyperthermophilic range, there is very limited tools available to access and modify these organisms. But this was successfully established, and there is also quite numerous publications of the work that was done with this organism. Furthermore, with this platform, we also tested in combination with real off-gases. For this one, it was done at 1 liter scale only. For the other ones, we went to higher scales. And we noticed here that with the real off-gas, similar performances were obtained as with pure CO2, which is evidenced from the comparable hydrogen production rates and also the lactate yields. So actually, this platform turned out to be quite tolerant to the impurities that were present in the selected off-gas, and no pretreatment was needed to directly process the off-gas. Then apart from the 3 microbial platforms, we also looked into 2 technologies, quite comparable, I think, to what was done in the BIOCON-CO2 project. So the first one, bioelectrochemical systems, the second one, fermentation. First one, of course, using renewable power as a direct input of energy. In the second one, going or using the renewable energy to first split water and generate renewable hydrogen as the energy source for the conversion of CO2. Maybe first a few words on bioelectrosynthesis. I think the principle was already explained by one of the previous presentations, so I will not go to that again. What the University of Girona, in this case, has looked into was to complement the in situ hydrogen generation, but the abiotic hydrogen generation that typically comes from water splitting, by also looking into adding or inoculating with additional cultures that stimulate or that bring extra biotic hydrogen production. So they have screened quite a lot of bacteria. I only show 4 examples here to see which ones would be relevant or helpful in increasing the actual hydrogen production rates in such a setup. And the optimal organism turned out to be the Sulfovibrio packaceae. Also, this has been documented in publications, so these can be consulted if you're interested to know more about that. A second point of work for University of Girona was to look into thermophilic bioelectrosynthesis systems. The idea there was that we needed then less temperature reduction on hot flue gases, that potentially reaction rates would be higher, contamination risks would be lower, product specificity may be higher, and also heat management would be more easy or more, let's say, energy efficient in this particular case. This has also been published, but maybe to show some results here, you see here over time a number of bioelectrochemical systems, that have been inoculated and cultivated for a long duration to see how they would perform at these thermophilic conditions. And you see here for the first 2 reactors in the more grayish colors. Yeah, I think I have to try like this. In the more grayish colors, that over 250 days, and there has been a gradual increase in acetate. Then at a certain point from these reactors, 2 new ones were inoculated, which are in the more bluish curves here. Again, we see increases of acetate over time. And after the 3rd transfer, we actually see a very strong increase in this case, the acetate production rates in these systems. Maximum rates are 28 grams acetate per square meter per day. It's not that excessively high yet, but a nice result, I think, for this type of technology. And also very high coulombic efficiencies could be reached up to 90%. Finally, University of Girona also designed and commissioned a pilot plant, which is quite unique in the domain of bioelectrochemistry, apparently. So they have 2 parallel lines with a lot of online sensors to measure dissolved CO2 and hydrogen concentrations, to supply the gases in a liquid phase before they send it actually to the bioelectrochemical systems. And so this unit is now available, of course, for follow-up projects and for further testing extensively in the domain of CO2 conversion and beyond. Then we go to the fermentation processes. In this case, we are all aware that gas solubility is limited, and that one way to increase the gas solubility is to increase the pressure on the system. So this is something that Vito has been investigating. Then we first, we were focusing on the moderately elevated pressure range between 5 and 10 bars. And first did a check in literature on what is already known about effects of pressure on gas fermentations. And then you see a diverse set or a limited set also of information on thresholds that exist in terms of maximum or total pressure or partial pressure, some inhibitory effects associated with hydrogen, with CO of course as well, sometimes with dissolved CO2. And on the level of process operation and control, in fact, very little existing sensors that allow to monitor and measure dissolved gases at elevated pressures. So there is really a lack of sensors to be able to understand very well what is happening, because ideally we of course want to know the dissolved gas concentrations to understand what is happening at the level of the microbial cells. So overall, for these fermentations at moderately elevated pressure and using C1 gases, a quite underexplored area where still a lot of work remains to be done. So we designed and commissioned a fermenter with a lot of auxiliary equipment with it, and also equipped with an online gas chromatograph to monitor the headspace continuously online, and also to control the gas supply based on the online measurements. The unit has a lot of features which are summarized here, so we can in fact accommodate all potential gases, syngas, real off gases. This is all possible. We can operate at constant or variable pressures. It's food-grade equipment, compliant with ATEX requirements, and has a lot of online process monitoring and control, including membrane filtration unit and of course headspace analysis. To give you an idea about the type of experiments that we have done, for instance, in one of our experiments, we have varied the total pressure and aiming at increasing the partial pressure of hydrogen while keeping the partial pressure of CO2 constant, and then look into the effects that we could see on the main product that we produced and on the productivity that was obtained. And then you see here, when we look into the same duration of the fermentation, then in fact with the increasing partial pressure of hydrogen, so at the increasing pressure as well, that the main product concentrations were maybe slightly decreasing or stable, and that the productivity is also, let's say, more or less the same. So for this particular conversion, our conclusion was that hydrogen transfer was or did not seem to be the main limiting factor, and that maybe some limited inhibitory effect was there linked to either the increase in pressure or the increase in hydrogen partial pressure. So that was not 100% clear what would be the main issue there. And we also did not see any changes in the product spectrum of the conversion that was studied here. Then in terms of product titers, so you saw on the previous slide the product titer of 20 grams per liter. Actually, we want to go to much higher product titers, 40, 60, 80 grams per liter ideally. And Arkema, a project partner, looked into purely from a reaction enthalpy perspective for lactate and isobutene, for instance. If we make that from CO2 and hydrogen, what would be the temperature increase, the adiabatic temperature rise, if we do not implement any cooling in our fermenter? And then you see that depending on the product, going to product titers of 60 grams per liter and beyond, we see substantial temperature rises, meaning that we would have to implement cooling. In principle, it's no problem, but actually the heat losses that may not be detectable or meaningful at lab scale can become quite substantial at industrial scale. So which means that for a 100,000 ton lactic acid per year production plant, energy consumption comes close to the energy consumption of 14,000 Europeans. So based on that, and because of the limited use of waste heat at a temperature of 35, 37 degrees in the mesophilic range, the idea is actually, or the interest would be to go more into the higher temperature range, and that's why we have these thermophilic, hyperthermophilic organisms that could be of interest from the perspective of the heat management in such reactions, focusing or starting from CO2 and hydrogen. So that's an important one to keep in mind here. Of course, the higher the temperature, we come in issues with the gas solubility that will be reduced, and maybe then we have to increase the pressure again to compensate for that, and so it becomes also a more complex story than only the temperature and the heat management alone. Main reason for this heat release is, of course, the use of hydrogen. If we had alternatives for hydrogen, such as methanol or ethanol, the situation looks quite different, but then of course we need to have microorganisms that are capable to convert the combination of methanol and CO2 or ethanol and CO2. But I think it's worth exploring also alternative metabolic routes than the ones that we have or that we are typically looking at so far. So on the CO2 conversion technologies, there is a number of flexible prototypes available for the pressurized fermenter. Studies have already been done for over 1.5 years. We've also done tests with real off-gases in the system, and we have run experiments up to 10 bar A. And of course, we identified that for CO2 hydrogen combinations, reaching high product titers may come with issues in terms of heat management. I'm not sure, Anna, how much time I have left?
We have time.
5 minutes or so?
Yeah, something like that. Yeah, 5 minutes. Yeah.
Yeah. Okay. So there was also some modeling work done by IDNR. They developed mathematical models using an open source environment of Open Modelica, which had the advantages that it has a modular structure or architecture, and that specialized solvers are available to solve complex problems, and that also a connection can be made to open source Python for model calibration and optimization. So the mathematical modeling constituted the various steps into the whole process, so both the capture step, conversion step, and separation step. And in addition to process models for each of these, also thermodynamic models and metabolic models were integrated as needed. So the progress beyond state of the art for the modeling and simulation work has been that with the integration of thermodynamics into the capture step, that we could actually very well simulate and also reach and replicate the performances that are there and that have been reported for the actually used solvents and amines, and that they can also be used then to the novel tailor-made solvents or mixtures that we have developed in our own project. So there has also been, for the first time, quite comprehensive modeling on bioelectrochemical and biological systems, including physicochemistry, microbiology, electro and bioelectrochemistry. And this simulation tool has then also allowed to simulate a number of scenarios in the project, and also indicating which would be interesting ways for further upscaling and improving the various technologies under development. Then as a last item, I would like to touch a bit on social acceptance of products made from CO2. And here Nova Institute was the partner who looked into this. And they were interested in getting the perspective of industry that is already producing products from CO2, and to see what they think about social acceptance of these products by consumers. And on the other hand, by the consumers themselves, how they feel about using products that are being made of CO2. So the methodology that was used was to perform first the literature research, and then to do an online survey with a number of companies, also some interviews with company representatives, and then finally also to do some discussions with focus groups of consumers. So first, maybe on some literature information that is there. This is actually a topic that has not been studied too much. There are a few studies, but that's about it. In general, the general public is thought to be more positively oriented towards new technologies such as carbon capture and utilization when they have already a rather high environmental awareness, when they have a more technical background, or when they are younger. So the age of people also determines to some extent how much or what their attitude is towards these kind of new technologies. And the acceptance and the trust in such technology strongly depends on who is providing the information. And then in Germany, in this particular case, particularly the government and NGOs are considered then as the most trustworthy sources. There is always the not in my backyard effect, and this has not only to do with being close to a place where the technology is being implemented, but also more if there is health issues, contact with skin, sleeping on a mattress made of CO2, then such things also pop up and may become an issue. So as take-home messages for the interaction with the companies, they usually find it difficult to market their product as being an outcome of a carbon capture and utilization process, so they don't use that in advertising that. They are looking for a simpler technology to get such messages across, maybe thinking about circular carbon and things like that. And brands, or involvement of brands, is a much stronger driver than actually regulation, apparently, to get these products and to get more publicity on these CCU products. Then on the consumer side, these the various focus groups received materials made from CO2. They did not know upfront that they were made from CO2. And then they were happily surprised when they were informed afterwards that this was actually materials made of CO2. So they didn't know much about it, were positively surprised about it. And then it was confirmed that their trust would depend also on who's providing the information and also in which way the information is shared. And then particularly when it was about maybe creams or soap to be used, coming in contact with skin, then maybe people would be a bit less eager to use it, although upfront, if they don't know, they don't see any issue in doing that. So with that, I want to thank the various partners involved, the European Commission, of course, for the funding. And I would like to refer also to the project website, where all the publications can be found and where also detailed presentations are there, because we had our final webinar last year already. So all these detailed presentations are freely accessible over there. So thank you for your attention then.
Thanks, Helene. When is this project finished? Because
end of December.
End of December, but I think we started all together, so you didn't have an extension. Okay, you didn't prolong. Okay, because we have an extension of a half a year. Yes.
I know most projects did. We shortly discussed about it and decided not to do it. So I think we achieved most of what we wanted to achieve in the 4 years. Yeah.
But this is really, some approaches are very similar to ours. So some of the things are really nice. It's really nice to see how the parallel and complementarity. Yeah. So are there any questions? No, I do have a lot of questions. Yes, yeah, but we don't have much time because we go to the. But I would like to know how was this study done on the social acceptance? Was it with asking people directly or online questionnaires? How was this done? Do you know?
So first there was an online survey. So their Nova Institute launched it only online to their industrial contacts. Then they had, I think it was also online interviews with selected industrial representatives.
Okay.
But with the focus groups there, it was really physical meetings. So I think they selected a group of people that would have a higher environmental awareness, and then others with a lower environmental awareness.
Yeah.
And they received 4 samples of products that were made from CO2, but they didn't know about that. And then they were just taught to look at it, give a bit their feedback on what they thought about it. And then during a physical session, different means to convey information about these products were used. For instance, a scientist giving a very complex explanation about it,
okay.
or a very, let's say, a YouTube type video that was made. So 4 different ways of conveying messages about it to understand what they would find the most interesting one. And then so they were gradually made aware of the fact that these products were made of CO2. Okay. And then of course when it was a soap to use on the skin, yeah, they felt different about it than when it was maybe a toy to play with, or something, or a cleaning solution that was used. So that was quite different than in terms of the type of product that they had received.
Okay.
But that was physical with a few people. So it was each time with 4 or 6 consumers, let's say, that this was organized. Yeah.
Okay, yeah, thank you. So I will ask you my technical questions later on, so we can go on with the panel, because we have now a panel discussion. Okay, here they are. Hi, hello, can you see us? Yes? Okay.
Yes.
I think, Helene, maybe we can sit. Yeah. Okay, so I think we can see each other now. Now, thanks for coming online, but to take your time to join our event. I will close the. Oh, this lady. No, but that is a lady. Yeah. Okay. So, yeah, welcome. We have now a panel discussion in which panelists are involved, and they are scientists that are involved in several projects that they look very much like the BIOCON-CO2. So Helene has explained BioRecover, but they are working on other ones, and I would like to ask them to introduce themselves shortly, and to explain a little bit your background and a very short speech on your project. So I think we can start with Albert. Yeah, I see you here in the center of the screen.
Good afternoon, can you hear me?
Yes, we can.
So my name is Albert Isasola, and I come from the Chemical Engineering Department of Universidad Autónoma de
we don't see them.
And I'm the coordinator of this project called Vivaldi.
They cannot see us.
And the main objective of Vivaldi is to use CO2 emission from bio-based industries. So it's a H2020 call based on bio-based industries. And our objective is to go from CO2 to added value organic products. So we are going for itaconic acid, succinic acid, lactic acid, and 3-hydroxypropionic acid. As you see, they have different market shares. So we have lactic acid, which is with a lot of market penetration, succinic and itaconic, which we believe is the present of organic acids, and 3-hydroxypropionic acid, which is a a future with a lot of possibilities. And this project starts from CO2, and basically, to be short, because it's difficult to make short such a big project, what we do is an absorption of CO2 with enzymes. Then we do electrochemical reduction to intermediates. In this case, we chose formate and methanol acid. And methanol, formic acid and methanol. And then there is a final biological step with Pichia pastoris, which is a methylotrophic yeast, and this Pichia pastoris transforms the methanol and formic acid to the organic compounds. Of course, there is a last downstream process. So the idea is absorption, a first fast with high intensity electrochemical conversion of CO2 to let's say C1 building blocks, and then a biological conversion to more complex products.
Oh, it is this. No, it was perfect. Thank you. Yes, I have a question. And until which scale are you planning to work on the fermentation, for example?
The fermentation, we are going to reach 10-liter fermenters. So it's well, Pichia pastoris is a well-known yeast, and that is the people from papaya process they know a lot about that. So the difficulty will be to select the strain that does exactly what we want. So that starts with methanol and finishes with succinic and carbonic acid. This, of course, requires a lot of previous lab work. We have the people from BIOCON in Vienna, and also people from UAB that are experts on Pichia pastoris. Yeah. And then, at the last year, we are going to go for larger fermentation processes, so that we have enough material for the downstream and the industrial validation of these products.
Okay. Thank you very much, Albert, for the introduction. Yes, we'll continue with Konstantinos Atsonios. He's coordinating the Biosphere project.
Yes, thank you. Good afternoon all. I have prepared some slides if I may do so. If I don't have time to show them, otherwise I will I can make a short presentation and like Albert.
No, I think if it could be possible, if you just give a short pitch.
Okay.
Yes.
Okay. I am Konstantinos Atsonios. I'm from CERT, Center for Research and Technology in Hellas, and from the CPRI Institute. I'm the coordinator of the Biosphere project. The Biosphere stands for the biofuels production from syngas fermentation for aviation and maritime use. The concept of the Biosphere deals with a combination of advanced thermochemical and biochemical pathways, where starting from the valorization and conversion of biogenic residues and waste from various origins, and converting them into syngas. And syngas is the feed stream that is converted into a novel two-step biological process into microbial oil from triacylglycerides, and then the triacylglycerides that goes to hydrotreatment for where the final destination is the production of drop-in biofuels for maritime use. The project is an Horizon 2020 project, and starts in April of 2020. And the main target is to bring this novel technology at TRL5, meaning that we aim to produce 2 barrels of advanced biofuels, drop-in biofuels that can be compatible for aviation and maritime. That's all from my side. If you have any questions about the project, I'm happy to discuss. And I would also like to add that the BBPP is also the key partners in the Biosphere project, and I was invited by BIOCON. As also like BIOCON-CO2 project and Biosphere, the core technology is the valorization of biochemicals and biotechnological processes into advanced biomolecules like triacylglycerides and microbial oil as well.
Yeah, thank you, Kostis. The project is halfway, isn't it?
Yeah. Yes.
Yes.
Indeed.
Okay.
We are running at the third year of the project.
Okay.
And
Thank you.
yes, now we are in the stage that we are developing the large-scale tests towards the optimization of the novel biological processes.
Okay, thank you. And the last and not least panelist is Ignacio Herráez Chamorro. Ignacio, are you there?
Hi. Yes, I'm here. Hi.
Okay, I see. Okay.
Yeah. Well, first of all, I would like to thank the BIOCON-CO2 project for giving me the opportunity to present the Back-to-Foil project. Okay? My name is Ignacio Herráez. My background is as a chemical engineer and biotechnologist, and I'm working at NanoGap. NanoGap is a spin-off of the University of Santiago de Compostela, and we basically manufacture nanomaterials for the petrochemical sector mostly, and now we are focused on renewable energies. The way we do is we manufacture atomic quantum clusters that are able to enhance catalytic reactions by photocatalytic reactions and heterogeneous catalytic reactions and so on. Okay, and I'm here to, on behalf of the Back-to-Foil project, which is an EU-funded project where our aim is to demonstrate the possibility to produce added value products, ethanol, butanol, hexanol for the transport sector from a source of CO2, water, and sunlight, using enhanced bacteria that are modified to optimize the energy, okay, that is able to transform from CO2 and hydrogen into alcohols. Basically, the project is divided in two technologies. The first part is a photocatalytic process where we use the sunlight, the energy from the sunlight, to water splitting by using these atomic quantum clusters. These atomic quantum clusters are a group of just a few atoms with a specific geometry that are able to absorb not only in the UV but in the visible, producing hydrogen. Okay, this hydrogen will feed a bacteria in a second step in a fermentation process that are transformed into alcohols. This second part is a bioelectrochemical system that are steered by an electrochemical cell that where we steer and control in a better way the reaction. We also harness this to produce in situ hydrogen generation that Eileen has explained before, and also we optimize gas diffusion electrodes for a better diffusion and transfer of the gases within the bioreactor.
Okay.
We are at TLL5 at the end of the project, and we got an extension, a 6 months extension, and we finished the project in July. So just 15 days left.
Okay.
We are running some experiments, and we will be glad to present you more or less the results in the panel discussion.
Okay, thank you. Thanks a lot, all of you. I see that the most of the panelists, they are working already some years on CCU, so that's very good. So we can have some interesting thoughts on from them. I would like to start because we see that we have started at BIOCON-CO2 with very low TRL, but we already have some insights of what works and what doesn't work so far. So I would like to know from the panelists which scientific advances do you think they are needed in order to improve the conversions that we have already at the state of the art? So I would like to start with Helene, maybe.
Personally, I think it's still both at the level of the microorganisms and at the level of the process. We still need to improve, I think, in terms of titers that are being achieved. And you may say that's already in the direction of increasing TRL levels, but I think scientifically there is also still a lot to discover still on how we can reach that and what the problems are to get there. I think what we also see in the reactor systems, I think a lot more knowledge is needed to understand how we can balance the demand for the gases over time and under variable conditions as they may occur in the processes versus the supply of these gases. So I think for me there is still a number of items to investigate both at the level of the organisms, looking into alternative microbial platforms. I think I gave some hints already in which direction that could go. Looking for alternatives for hydrogen, improving mass transfers, maybe some other concepts on reactors that might still be developed that can be better than what we have so far. But I think really understanding at the metabolic level and how we can balance supply and consumption under a variety of conditions in the gas fermentations is but a few things I think that still require further development.
Yeah, I think Albert, you are more involved on fermentation of C1 soluble products using Pichia. Do you have some hints? Where do you have your bottlenecks?
Yeah, I think that if I see it from a chemical engineering perspective, I think that the three aspects that we need to improve is the mass transfer. Because if we want to use CO2, then CO2 is a gas, has low solubility. Then what we do is moving it to a liquid phase or just transform it electrochemically to a C1 so that it's in the liquid. But ideally, it would be very nice if we could work directly with CO2. But that means, this kind of mass transfer issues because you work with the gas and with the liquid phase. Then also, from a chemical engineering point of view, there are two aspects that we need to consider, which is rate and which is stoichiometry, kinetics and stoichiometry, which is the basic. Kinetics with CO2 are very difficult if you go directly to the biological processes, because you know that microorganisms that live from CO2, they are very slow. So then I think that the first electrochemical conversion of CO2 is very good, because then you have here a rate. Because electrochemistry is rate. But the problem with electrochemistry is the second aspect, which is the stoichiometry. You cannot have what you want. With electrochemistry, you only have C1s. So then is when biologically enters. So I think that a combination of electrochemistry and microbiology can overcome these two issues. So electrochemistry will give you kinetics, and microbiology can give you yield and plethora of different substrates.
Thank you. Thank you. And Kostis, do you have any thoughts on this?
Yes, as the first step of our biological process is the aerobic fermentation using Acetobacteria strains. The main bottleneck is that, as Ellie says, the very low acetate yield. Acetate is the intermediate process. And as concerns the second step, which is the liquid fermentation in under aerobic conditions. Here the problems and the main bottleneck is the low carbon utilizations, where also so far we observe a low lipid to biomass ratio, and also as considerable part of the carbon is transformed into CO2 and goes out of the process. And the alternative, the solution that we are aiming to use it to address to tackle with this issue is first to use continuous to use the reactors under continuous mode and also adopting cell recycling. The first and the second very important asset is the metabolic engineering, making the necessary transformations into the genomes in order to increase the yield and also the purification, the selectivity of the target molecules.
Okay. Yeah, thank you. And Ignacio, from the Back to Fuel project, do you have some insights on this? Because I see you are focusing only on BESS systems.
Well, we also has a partner, Wageningen University is the one that is in charge of the enhanced bacteria. He modified bacteria by biological methods, conjugation, CRISPR, and so on.
Yeah.
And what we have seen is if we want to produce, for instance, ethanol, if we compare it to the commercial scale that are using from CO plus hydrogen, our reaction is hydrogen plus CO2 has some additional challenges. So thermodynamically is a difficult conversion. So in my opinion, I agree with him. We need to achieve reactor studies that show specific ethanol production rates using these strains that could allow calculations on yields and titres. So that's I think is the advance that are needed from our side.
Yeah.
From
Okay, thank you. And because we have had just some minutes ago the presentation from BioRecover, and I found very interesting. Helene described the use of some thermophiles for production for utilization of CO2, and you described Thermotoga species. Can you explain a little bit more what are the advantages of using Thermotoga or mesophiles in general?
I think some of the advantages I already indicated when when I started introducing the bioelectrochemical systems that were tested in the thermophilic range. So you can expect maybe less contamination issues, although maybe on CO2 hydrogen that's usually not that big of a problem. Maybe increased rates could be there, better thermal management. So I think there is a number of potential advantages for Thermotoga. That's even more the case because there you go to 80-degree range. And I think for Thermotoga, the interesting thing is that you combine CO2 with an organic carbon source.
Yes.
To then make a product, okay, it's only lactate and hydrogen at this case, and then hopefully in the future more products can be made from it. So that's a bit limited at this moment. But I personally like to look into novel microbial platforms and maybe different routes to valorize unorganic waste stream together with CO2 into something else. So maybe these mixotrophic approaches also still have things to offer. And then going indeed towards other temperature ranges as well.
Yeah. How would you define an approach to find new organisms that will do what you want? Would you search for them in some specific environment, or how can you do? How would you do this? Maybe, Albert, you have some ideas on this, or?
That's a very good question, and I have to say that I am simply astonished of the work that biotechnologies do. So this is not my specialty, the genetic changes. So when I listen, I found a strain of Picapostorius that can produce, for example, a very low amount of succinic acid. But what we are going to do, we are going to block this gene, we are going to amplify the gene, and they start changing the metabolism, and then you end up with a strain that can produce a lot of succinic acid. So they change. They play like God, so they change the symmetry of the microorganisms and they fuse producing a lot of things. So I don't know if it's what do we have to do, but if you know the metabolic pathways of your culture, then you can adapt them and you can change them either. So myself would be through operational parameters, but they do it in a lab scale, and for me it's a combination of both. So that's how I feel when I listen to them. I feel like they are playing both.
Okay, thank you. Are there any more thoughts on this?
Well, but we use research on literature, and we start the project with different mixed cultures, and then we pass to pure cultures. We go from one type of bacteria to the other, and then we knock out some pathways, and then we play as both as a recess.
Yeah.
The people are Wageningen. But then the goal is, once everything is done, see if it is the bacteria is growing well, and so on. So it's too complicated to find out the right pathway, the right method to accomplish it. If we add also all the pandemic and all this situation that has stopped too many experiments, so it's a complicated thing. So, but I think searching on literature and see also what other institutions are doing, and then try to see if you can do something different or adding something else, I would say.
Okay. Yeah, thank you. Also, I would like to know from the panel, or maybe if there are any comments on the public, please just raise your hand and also give your opinion or any comment, or if you have a specific question, please do so. I see, and we know all that the downstream processing of the products is really important, and we have in all the projects there is always a part on it, but we can see how difficult it is and how low titers we are getting. So I would like to know from the panelists what's their opinion on the challenges that we have on the downstream processing. Do you see any potential on using the fact that the substrate we are working with is not soluble but is a gas? When we are producing some volatile products, can we combine in some way the specificities of the gas fermentation with the downstream processing? Helene, do you think?
I think concepts have been investigated to see whether it makes sense to do it. What I see a bit as a challenge there is that on the one hand, you want to supply your substrate gases under optimal conditions. So you would need a system in which you supply the gases in one place and make sure that they are fully consumed at the place where then maybe the gaseous product appears in a headspace or so, and then you can of course recover it because it would be there at a high concentration. And I know Electrogaia, for instance, they managed to do that, to produce methane that is nearly 90–95% pure, I think, from CO2 and hydrogen. So it is possible, I think, if you have very well developed and optimized your process. But otherwise, if you are not there yet, or you have smaller lab scale systems, I think it's very difficult to come there, because you want to supply as much gas as possible to get your reaction going and your conversion, while you also want to have a very high product concentration also in your headspace to recover it in an energy efficient way. Or you need to have very different product characteristics that allow for an easy separation.
Mm-hmm. Okay.
But so these are a few thoughts on the gaseous phase. Usually I would say it's more interesting when your product is in a different phase than your substrate.
Okay.
I would think, but not always. So,
no. Okay, I understand this. I think, and in the back to fuel project, they are also working on butanol, ethanol, hexanol. So that's also similar products we are working in. And are there any thoughts on downstream processing of these on these products in that project, Ignacio?
Well, here as Kevin says, is the tricky question when you produce several products, and at this lab scale it's not easy to arise this question, because it's not easy to first produce the three of them at the same time, and also, as I said, they grow in the bacteria. The bacteria for us is the most disruptive point, not the rate of the production products at this time, because achieve these grams per liter or this titer at the end of the reaction, it makes to handle a lot of variables behind. That this is a part of a question that we are not on the table. But I would say it is not easy when you are handling bacteria, because there is a moment when you are producing CO2, hydrogen, acetate, ethanol, but then it goes down, and then acetate is more produced than ethanol. So it's not easy. It's not easy to answer.
Yeah.
From a lab scale point of view.
Yeah. Thank you. For the lipid extraction at the biosphere process, do you have any limitations there, specifically because you are working with acetic acids?
Yes, indeed, the great limitation in the downstream processing for the recovery of the lipids is the high energy demand and the very energy and needed in order to retrieve and recover the lipids that is intracellular within the yeast. And this is a very energy and demanding in principle, and according to the state of the art. As far as we are developing novel techniques to break the cells of the yeast, like steam explosions and membrane separation techniques, but it's a great challenge for us. As initially we expect a high energy demanding process for that. And also we expect also the metabolic engineering tool to help that and make the reactions and of the cells work to break to reduce the reaction.
Okay, thank you. Helene?
Maybe to add shortly, considering that in regular fermentation, downstream processing goes already up to, what was it, 70% of the costs. I think in one of the presentations it was shown, we have to get with the gas fermentation to the same ranges of titers, 50 grams per liter beyond, otherwise it makes no sense. That's my opinion about that. And okay, we do research, we first investigate things, but we also have to think about the consequences in terms of costs. So we will have to get to the same performances as for the other fermentations, because also there, the downstream processing already costs a lot, I think, or contributes a lot to the costs.
Yeah.
So.
Yes, we are with the.
Can I add something?
Yes, please.
I think that something that I wanted to add, and something I like about our project, is that we work with yeast, and one of the reasons that we work with yeast is that they can work at a very low pH, and that was done because the downstream of organic acids is very much easier at a very low pH. So I think it's good that you have to think that the process goes together with the downstream. So when you have low organic when you have organic acids and you want it to be like proton, so you work at a very low pH, and that's one of the reasons that among all the different microbial platforms we went for yeast.
Yeah. Thank you very much. I would like to discuss a little bit on electrobiochemistry, because we are mentioning a lot, and also we have an expert here in the audience, and Elaine as well, and others. So this electrochemistry in general is coming up, and electrofermentations too. But I would like to know the opinion of the expert on this technology. What is now the bottleneck of this technology, or what is the potential compared to normal fermentation? I mean, we have seen you obtain some higher yields in BIOCON-CO2. We obtain a little bit more product, but what is the expected increase or improvement of the process? Maybe Ignacio, you know about that?
Yeah. Well, I think the bottleneck is the solubility. And within the back-to-fuel, Elaine can help me with the answer, but we have overcome this by increasing the pressure.
Okay.
Elaine has explained very well in the previous presentation that well, in order to avoid this low solubility, by increasing the pressure of the reactor, we can increase on or overcome this possible bottleneck. And this is what we are doing within back-to-fuel. Pito actually is performing at this moment at around 6 bars and then 10 bars.
Okay, so what you say is a combination of pressurized fermentation and electrochemistry?
I think one of the benefits is that you have this in situ hydrogen production. And maybe without having the gaseous form, if you properly do that. So that could be beneficial. But of course, at this moment, there is still a way to go to reach also high titers, high productivities, and so on. So if you compare that with regular fermentation, I'm sure there will be applications where this is very suitable technology, but there is still a way to go, I would say. So I think it certainly has its benefits, but we're not there yet, maybe. So for CO2 conversions, I mean. So there's other ways. That's a bit my opinion, but maybe the people in the room have a different view.
I don't know. I am looking to Daniele, but Daniele
is discussing.
Is discussing. Yeah, Daniele, we are discussing on electrofermentation. What are your experiences in the project? Because we have nice results on electrofermentation, but we were not there yet with the gas fermentation, but we applied it to sugar.
We applied on AB fermentation, not with CO2. And, well, on a different approach in other projects, for improving anaerobic digestion, but we did not work so far with pure CO2.
But until now, the results are being positive.
Yeah,
but
in terms of bacterial growth rate, of productivity and selectivity towards a target product, for example, in ABE towards butanol.
Yes.
We saw that applying a certain potential to the cathode, we could improve the selectivity of the process.
Okay. I think maybe that is also nice what you say. Maybe because we have in situ hydrogen generation, then we can go towards certain products. I didn't see that way before. Yeah. Okay. Thank you. Any other thoughts on electrofermentation? No? Okay. So then I think we will be wrapping up. But I have a kind of general question from for the panelists, is because we are looking here at the technologies, but it's good to look how can we integrate such a process in time. So we have discussed also before and in your presentation and in the other presentations, where are we going to locate the process? Are we going to go to the point source of CO2, or are we going to go somewhere else where the where the products will be made? And I would like to know where you see the most interesting opportunities. So if you say, I think such a CCU process, where will it be the first implemented with the knowledge that we have now? So maybe Kostas, what do you think about that?
Well, I think that it would be also, if the question is has to do with biochemical and electrobiochemical process and compared to the other competitors of thermochemical as well, I think that since the greatest advantage of that is that potentially enhances great selectivity of the target and the valuable end product. I think that at first this technology could find a very good ground in refineries, especially now where the regulation is to move towards advanced biofuels with and tropical biofuels and forgetting co-processing approaches, etc. And at first that also, of course, as we see that most of the biological, biochemical processes works better if the feed gas contains both with carbon monoxide and carbon dioxide. I find steel industry and off gas and coke oven gases as the first and most the greatest candidate for the first implementation of such a CCU concept. That's my point of view.
Thank you. Albert, for the Vivaldi concept, what do you think will be the most, what will be the most potential implementation or the easiest?
Well, in our project, the call was based on bio-based industries. So what we are focused is in industries that are bio-based and that they produce a compound. So the perfect candidate would be a company that emits CO2 and then that, for example, requires to buy lactic acid or itaconic acid. So that's the perfect match of the circular economy. But we know that this is difficult.
Yeah.
What we have observed is that these kind of bio-based industries have two kinds of CO2 effluents, let's say. If they, as they are bio-based, some of them they have fermentation, for example, for the bioethanol or for the brewery, and these CO2 emissions are 98, 99%. So this is very good because it's almost CO2, it's very easy to go into the liquid phase or even to go directly to an electrochemical reactor. That's the perfect scenario. And of course there are no toxics or pollutants for the microbiological process because they come from biological process.
Okay.
But then there are other CO2 effluents that come from another parts of the plant, 15%, 18%, with potential pollutants, salts, NOx, whatever, and that is more difficult because that requires pretreatment, particularly if you want to go to electrochemistry, because the metals that are on the electrodes can be damaged because of the pollutants. So I see a double scenario here, depending on the, maybe that's very obvious, but if the effluent is 98%, 99% CO2, that's perfect.
Okay.
If you want to work with gases with some pollutants, then you have to think a lot about the pretreatment and the potential detrimental aspects of a posterior electrochemical reduction of this CO2.
Okay, thank you. Yeah, thanks a lot. Helene, just to finish, do you have any thoughts on this or?
On this particular topic, I don't have anything specific to add. I also am very much in favor for these hybrid concepts as well. I think they offer then the opportunity to do your initial CO2 conversion at the place of the emission, and then you have maybe a liquid energy dense, hopefully, that can then maybe be
potentially transport it even to another place if you wish, or if there is an interest to do that. So that decouples maybe also the potential locations of it. Yeah.
Okay. So in view of the time, I want to thank all the panelists and also the public for the attendance, and yeah, so I can close the session. Yeah, okay, thanks a lot, and I hope you enjoyed. Yeah.
Okay, thank you.